Hello everyone, I would like to welcome Dr. Marco Zullich. He's going to be speaking to us about explainable AI.
Yeah. Hello, everybody. So we're still missing some people here in presence, but I think we can start maybe by soft introduction. So as you can see from this slide, today I'm going to be talking about explainable AI, and the presentation is roughly divided into two parts. The first one is actually going to last only 1/3 of the time, and it's going to be a quick introduction to explainable AI. But then we're going to talk about the quantitative evaluation of explainable AI, and this is because XAI is not an oracle that lets us know what the model does. And we need to be able to find ways to assess whether the explanations make sense and are actually aligned with respect to the model. So this is the reason why I want to do this course. So I'm a lecturer at the University of Groningen. I have been teaching there in the last 3 years. I teach mainly object-oriented programming, trustworthy and explainable AI, and unsupervised deep learning. And my field of research is actually explainable AI, especially at the intersection with model compression, so ways to make your models smaller and faster. From 2026, I'll be starting a new position as an assistant professor at the Technical University of Delft, still in the Netherlands. So, of course, I also like to talk about free time, and I would also ask you to introduce yourself, at least here in person later. I like mountains, so I decided to go in the place in the world which has most mountains, so the Netherlands. I do like hiking, climbing, and bouldering, and generically open air activities when there's like something resembling at least a hill. So, since we're still waiting for the other people to join, we can maybe just do a small round of introduction. So if you can say your name, where you come from, and what you're doing right now, and maybe also why you want to attend this course. Maybe you don't need to have a specific answer for that. So maybe we can start.
Okay, thank you very much. My name is Michalis. I'm doing my PhD here at the University of Thessaloniki. I'm a mechanical engineer.
Yeah.
To be precise, and I'm working on predicting aircraft engines performance with neural networks. So the course seemed very interesting to me, to make it faster and more explainable.
Yeah, that's all. Yeah, thank you.
I'm Emily. I'm a PhD student at the University of Glasgow in the search for AICET. My project is working with speech data and modeling information.
I want to, for me as well, I'm from Glasgow, fortunately, and researching. I'm working how music influences industry responses are in the middle of secret languages. So I find it relevant to my work in a way that I need to explain why people react in certain ways. So maybe might highlight some features for music that way I hope I can create some specific visual context. That's good.
So you seem to be interested also like in the inferential part of machine learning, not only on the prediction, but also on understanding the relationship.
Let's say that the majority is where I think we have. So at the moment, I'm just working on opposite. There is no like a specific asset on my work. But I would like to do some kind of condition model. Maybe when people have some specific condition, I can provide some interaction. So I divided into one condition model, so I can predict for people with having some fatigue disorders, have some kind of stress. And I can provide an intervention that is something that's going to figure out. But in the aspect of identifying how people respond to music, we would like to know if there is some certain way that we can quantify. How can we develop this kind of method that might be generalized on some way? So we want to see common patterns. So that's something that might explainable AI might know.
Nice. Do you want to introduce yourself?
Yes, Barcelona, University, and I know it's for trivial persons. Our project is about the translation construction. And I'm particularly interested in Barcelona because I would like to keep my work as much as still as much as this family, and also fair as behind we are aiming at abnormality detection and should be targeted to all kind of abnormalities and also kind of for grounds for the baby. So it's yes.
And it's really important, like say, you will also see an example where actually XAI was really helpful in having a bias if the complete failure of model.
Also bias also, but also that I think it might be very beneficial for me to explore the patterns because the modality is new, not very new, but 3D modeling is new a bit. So maybe the pattern, it might be helpful in pattern recognition. Also for the medical science as well.
See two new people. Do you want to introduce yourself very quickly? You can also say no if you're shy.
Yes. Hello. You want to start?
Yes, I am Victoria, and she's we're colleagues. We are undergraduate students. But we're conducting research about identifications and neural networks. I'm in the fourth year currently, and he's in fifth. He's graduating.
Nice.
I'm interested in solving combinatorial optimization problems using deep learning right now.
They're probably much better than me because I'm very bad at optimization. Is there someone from online, from Zoom, that wants to contribute a bit? Can they activate their microphone from home? So if someone wants to introduce yourself, but no pressure, and if you don't want to, we can start with a proper lecture. Let's wait for a few seconds. See, nobody is activating their microphone, so we can start. Good. So as I was introducing before, we're going to have a lecture which is divided in two parts, not of equal size. So the first part is going to take roughly 1/3 of the time. We're going to be talking about explainable AI, so we'll see the concept for explainable AI. So for example, what an explanation is, the types of explanation, and then in the second part, we're going to talk about feature attribution, which is possibly the most used and most important also explanation that we can have. Then after the break, we're going to talk about the quality of explanation, and we're going to be seeing specifically faithfulness, which is one of the most important qualities that an explanation can have, other quality facets, and also some other approaches, like for example, user studies and like the generalized taxonomy for properties of explanations. And feel free to interrupt me whenever you want to. This is meant to be an interactive session, lecture. You will see that I will ask a lot of questions to you. Fortunately, there's a few people here, so it's an optimal setting for being able to interact during the lecture. Good. So first, just a setup. I will not be spending a lot of time on it because this is meant mostly if you want to use these slides for self-study at home. You will see that there are some formulas. I will not be concentrating on the formulas, but this serves a bit on setting up the stage of what the symbols mean. So the setting is always the same. We have some data and we have a prediction. The data usually we suppose it lives in a d-dimensional space. We have a neural network, does a projection, which is usually nonlinear, and we end up with a prediction. This lives in a generic space Y, and this depends, of course, on the setting of the problem. So you all know the very basic neural network models, the multi-layer perceptron. So we have divided in layers, and the layers are fully connected between previous and in the next one. So again, we represent the D dimensions with these dots, which are called neurons. We have a hidden layer of variable dimension. We can have more of them, and we have an output whose size is dependent upon the task. We indicate with A the intermediate activations, which means the product between the values, the activation of the previous layer, the weights, and then we have optionally an activation function. And also we can decide to indicate the parameters, theta. In multi-layer perception, parameters are divided in matrices. each having as row the number of neurons in the next layer, as columns the number of neurons in the previous layer. I think it's all quite clear until now. One thing that I wanted to add with respect to the slides is the output. So depending on the task and also on the loss functions that you're using, the output can be for classification, either a probability distribution in case you use the softmax activation function, or before the softmax, you can have what is known as logits. Logits are real values which can be projected into a probability value with the softmax classification function. And this is important because in some cases you want to do evaluation of the explanations based on the probability values. In some other cases, you want to do it on the logits. And this can impact the way you actually do the evaluation later on. So for convolutional neural network, it doesn't change that much. The only thing that I wanted to draw your attention on is the shape of the activation. So before the activations were vectors. In this case, they're three-dimensional tensors or three-dimensional matrices. We have two spatial dimensions, which I indicate with HL and WL, so the height and the width. And we also have the channel dimension, which I indicate with the letter M. And this is going to be important later when we'll do explanations based on some intermediate layers. Okay. And now when we quickly set the stage, let's talk about why we want to interpret a model. So first of all, there's a fundamental difference which is quite recent in taxonomy, and it's a very difference between interpretability and explainability. So in this course, we're talking about explainability, and there's a reason for that. The interpretability is instead a fundamental intrinsic property of a model. So when we say a model is interpretable, it means that we can get up to a certain extent the reason why to a given input X, we have a corresponding output Y. So we can know, for example, the features that the model learns. So, for example, the basic building block for interpretability is the linear regression model, which is, you can draw it with a line. For example, in the one-dimensional case, when I have only one feature and one predictor, it becomes a hyperplane in a multi-dimensional setting. So the first question that I have for you is, given this linear regression model that you see on the screen, y hat equals 0.33x plus y. Can you explain, using your own words, what is the logic behind the prediction from this model? So what is the meaning of this coefficient? How do I go from prediction to, from input features to prediction? Yeah.
Probably there is an underlying correlation between the two.
Yeah.
And to what we see here, the equation says that y is correlated to deviations of x by 33%.
Yeah.
Plus a bias of 5. I don't know if that's the logic that you want to.
Yeah, exactly. I mean, that's exploring how you would explain this model to, for example, let's suppose you are a doctor, you're using this model, you have to explain why this model gave a certain prediction. You can see, for example, as a relationship between height and weight, for instance. Why your model says something about the patient that you have in front of you. And of course, as a doctor, you always are required to be able to explain what you're doing and why you think you might have a specific disease or you might be needing a specific medicine. So in this case, this is a good explanation in the sense that there is apparently a correlation between X and Y in this case. And basically the way you interpret this model is to say, yeah, do a unitary variation of X. So if I increase X by 1, Y hat changes by 0.33. And that is the basic explanation of a linear regression model. So if, for example, this could be like prediction of risk in insurance, we'll see later there is a law that says that you need to be able to provide explanations if you work in the banking sector or in the insurance sector to your customers, if this is an equation for establishing the premium, it's of course a very simplified example, and your customer asks you, why am I paying this much? You can say, yeah, because you had an increase in the variable X, so your price, your premium has increased by 0.33 times the increase of X. This is something we can do very easily with linear regression, so we can see which are the important variables. Usually, depending on the range of Y and the range of X, a very small value of the coefficient means that the variable is less and less important. So if a variable has a very small, important value, that means that you can usually scrap it from the model. And this is something we cannot really do with neural networks, because we don't have access to a natural way from the model to tell you, look, this variable is very important. In my case, this variable is not important. So you cannot explain simply a decision to a customer. And that's why you need explainable. And you probably know this chart. This is from a very famous book, An Introduction to Statistical Learning. If you're kind of new to machine learning, I highly suggest you read this because it's very simple as a book. The authors really did a good job in providing all the information in a very simplified way without losing too much detail. And this is the interpretability accuracy trade-off, or mainly interpretability flexibility, because flexibility is somehow tied to accuracy or to training set accuracy. It means basically a flexible model can learn a large variety of functions. So of course, deep learning is here. Deep learning can learn very complex functions, but also it is not interpretable. And we have this trade-off, which is a rule of thumb. It's not proven. There's not like a natural law, that the more flexible the model is, the less interpretable it is. And here you can see these squares refers to linear regression. The simpler the model is, also the higher its interpretability. So we find ourselves at a trade-off in which, if our model lies in like this right half of the chart, and we are required to provide explanations, we need to do something about it, because the model is not going to automatically have explanations out of the blue. This is why we need explainable AI to kind of approximate the complex decision making process of the model and be able to tell something to the customers. So now we know what interpretability is, but what is explainability actually? Well, the explainability is not a property of the model. So you say that the model is interpretable, not the model is explainable. The explainability refers to the usage of approximate tools to gather human understandable knowledge in a post hoc fashion. So let's go into details of these two words. Human understandable means that the explanation must be simple. You cannot use another model, another black box model, to explain a black box model, because that is essentially a snake eating its own tail. And you see actually a lot of work, maybe not now anymore, but not in like previous years, you had neural networks to explain neural networks. This is a concept that makes no sense at all. And also, it needs to be in a post hoc fashion. So it means that you explain after getting a prediction or a set of predictions. And instead, interpretability is there from the start. You already know that you will be able to have some rules that tell you how you can go from X to Y. Okay. So, what is an explanation? It's a very simple definition. You will find a lot of them, but for me, this is the definition that I like the most. Basically, whatever token of human understandable information concerning the predictive logics of an AI model. So, essentially, you see that we talk about generic AI models, but in the title of the course, you see neural networks. That is where this course will be added to. We'll not be talking about interpretable models, so you will not be seeing decision trees, you will not be seeing rule-based methods. that are very useful, especially in medicine, but we're interested in neural networks. And also, as a note, especially if you're studying this slide at home, every time you see like the math E symbol, we'll be talking about explanations. So this one over here. Okay, so why do we need explainable AI? Well, we actually had already a partial additional response to that from our colleague here, whose name I don't remember, because we have model debugging, regulation, but also like inferential study, which means that I want to understand the relationship between the variables. So I want to see which variables are actually leading, possibly in a causal way, my correlations in the data set. But we will see how we can use XAI for model debugging very quickly, and also we see examples of regulations. So this is a very famous example of a model whose bias led it to extremely wrongful predictions, and this bias was not noticed actually during the training of the model. So this is from 2018, so it's quite an old thing. Often you will see that when motivating explainability, a lot of people will talk about huskies and dogs and wolves. A lot of people will talk about tanks, recognizing tanks of like the US and the enemies. These are the first one is a toy example, so it doesn't really count. And the second one is just an anecdotal evidence of some general of the US, and it actually never really happened. So this is one of the first proper examples where explainable AI came in to help for debugging the wrongful functioning of a model. So in this research, these guys trained a model to recognize cancer in lung X-ray scans. And in the training process, everything worked correctly. The testing data set also was giving very positive feedback. I think it was about 85% accuracy, so higher than human clinicians. But then they realized that while deploying this model, the predictions were completely random. So they ran some explainable AI analysis. Specifically, these are also known as saliency maps or feature attribution. We have saliency map when you have them on images. And they actually realized that the model was looking very often at the shoulder. And you can see there are some markers here on the shoulder. So basically the model learned to associate the presence of a given marker to the cancer, the cancer label. Why this? Well, because the dataset was constructed in a very non-statistical way. And this is a very important thing in AI, which is often overlooked. You just, in machine learning courses, just learn to take all the data that you have, put it in a model without caring about its quality. So in radiology, it's very common for radiologists to use specific techniques, to use specific markers. And in this specific data set, all of the data of the people with cancer came from a specific lab, while all of the the X-ray pictures of people without cancer came from other labs. And this specific lab, they were using one specific marker present on the left shoulder of the patient. So yeah, the model used the stochastic shortcut, which is this term right here, to go from the features that were presented to the prediction. So do you know what stochastic shortcuts are? It's a term that I've heard also talked about in other lectures during this course, this summer school. So do you have an idea of what a stochastic shortcut might be? Yeah.
I'm not sure, but like the model learns something like noise, make decisions on this.
Yeah.
And uses features that should not be important for a decision.
Yeah, exactly. We are there in the sense that this explanation, you can rephrase it more generically, is this. So you have patterns, which can be both like real patterns, like for example, markers, or simply noise, present only in the training data and not in the real world scenarios. And they arise in mainly two cases. The first one is when you have a small data set. So even if the data set is very well curated, the neural network is so flexible that it can fit the data into multiple ways. more often not in a generalizable way. And the second one is when you construct the data set in a non-statistically sound way, which means you either create biases or anyway there are like patterns which are not really representative of the real life data. Then we can talk about regulations, and probably you might have heard about the right to explanation. This was first coined in explanation was first coined in the GDPR, in which basically states that users whose data is processed in an automatic way, they need to receive meaningful information about the logic, significance, and consequences of such processing. And so the user has the right to ask or to be informed by the company that processes the data, to be informed about how this data is processed. And of course, if you use neural networks to process data, you need to be able to provide these explanations. And this was later reiterated in the AI Act, especially for high-risk AI systems. The right of explanation is always there, but we also had previous regulations. In the EU, for example, the Solvency II directive of the European Union from 2009 says that in the insurance sector, you have to provide explanations to customers. And this is very common. I was actually working in Allianz, in the insurance company previously, in an office which was actually tasked to provide explanations to customers when their premium was higher than, for example, 20%. So we already knew that the customers would have asked, why is this premium so high for me this year? And we had to provide the premium. So it's not really a new concept in some areas of the market. Okay, good. So introduction on what is an explanation done. We can start talking about the types of explanation now. So we already briefly discussed about feature importance. And the question that we are actually answering is which features are considered salient or important for the model. It can be a generic rule, or it can be a specific rule for one prediction. So the goal is to rank the features and to give a coefficient of importance. Then we can have examples. So we generate new data, or we use existing data to explain what the model is doing. For example, we have counterfactual explanations or semi-factual explanations. Counterfactual explanations are basically answering the question, what could change the features to change the prediction? Or semi-factual examples is instead, what could change in the example, what can change in the data, so that the prediction does not change. And you see, for example, here an example of visual counterfactual. So we have a real image, which is predicted as a weasel, and we generate a minimum perturbation on this image so that the model, hello, please come in. So that the model can be classified, can classify this new image as a guinea pig. So we have a perturbation which is not that negligible, but you can see that it kind of makes sense. Like the setting is the same, but instead of the weasel, we have something which resembles a guinea pig. Of course, you can immediately see that it's AI generated. Yes?
I can see how this works in classification, but in terms of regression, where when you perturb the input, the output will always change. Do you use this type of explanation or not?
We'll see later. So remind me about your question later, because we're going to talk about counterfactual explanations. So feature importance and counterfactual examples are the two tools that we're going to talk about today. We're going to use in the examples, because there are also other tools which are sometimes a bit exotic, as for example, like the feature visualization here. Like for example, these are images which are generated from scratch, starting from random noise or from a fully white image, and you're trying to kind of excite the activations of some specific group of neurons. So you want to understand, for example, what is this neuron learning during the learning process of the model. Or you can have, for example, influential data points, like that would be you train a model, which data points are influential in changing, in determining training trajectory of the model, and which are data points instead are very prototypical, so they're not really influential. Here, there's an example from MNIST. These are influential data points in the left, and on the right, there are the non-influential data points. And you can see that actually all of the digits on the left side have something that makes them weird. So it is kind of important to run this explanation.
So you find about marginal data to see the action.
I don't know about the specific technique. There's a lot of different approaches. I think in this specific case, they were using a Bayesian approach. So I wouldn't be able to explain it right now. It's like trying to identify after the model is trained, what is what are the data points that were influential during the training. Other questions? No? Okay, good. So let's go into feature importance, which we already know. We can call it saliency-map, you can call it feature attribution. There's a lot of different words for the same concept. So we saw an example in images, but you can have an example also on natural language processing. For example, you know that ChatGPT and GPT models more generically, they are single token prediction models. So they work in a sequential way. You have a prompt, which is presented here to the left. To innovate, one should. And then the model needs to predict a certain token. And the model here predicts think. And this is a classification problem. So essentially, the model outputs a probability distribution. I choose either the most probable token, or I subset to the most probable tokens, and I do like a random selection according to some criteria. And I can also try to run a saliency to run a feature attribution in this case, and to get like this sort of distribution. Here I see, for example, that for predicting the token think, innovate is the most important token with a 0.7 coefficient, and also should is quite important at 0.25. After my prediction has been run, think is appended to the prompt. So the prompt becomes to innovate bunch of think. And then I have another prediction. In this case, outside is driven mainly by innovate again and by think, and so on and so forth. So this is a way I can do feature attribution. Of course, it's not a one single step as it was for the image before, but it is like a n-step approach. I also can also have feature attribution for generic data sets. Now, the quality of this image is not super nice. This is a very famous example, is a toy data set, a California housing data set, where you're predicting the price of some properties in California, and you have several geographical and demographic features. So you ask yourself, does the location of a property affect its price, which is the predicted price is $454,000. And what this plot says is that the average occupancy, so how many people are already living in that building, in the same building, is actually positively affecting the price of the property, but also the location, because here we can see that also longitude and latitude also offer a substantial contribution in the prediction. And of course, we know already from the images, you have your image, convolutional neural network, for instance, the convolutional neural network predicts bird, and I can ask to the model, why do you predict bird? And there are techniques. This is not something which is produced by the model, it's an external tool that highlights the areas, the pixels in the image that are most important for the bird prediction. And what is nice is that a lot of techniques allow me to steer the generation according to class. So I can also ask, why is this predicted cat, for instance? And I will see if the model highlights some cat feature in the data set, in the image. Okay. So on to counterfactual examples instead. So let's take this specific case. Susan is female. She's 32 years old. She lives in London. Her marital status is single, has been deemed responsible for 3 car accidents in the last 5 years. And for the year 2025, she had evidence in her car insurance premium of £1,000 as a result of being classified as a high-risk customer. So there is a model which says you're a high-risk customer, so the premium for 2025 increases. So Susan has a right for explanation, and she asks the insurance company an explanation on why the premium has had this dramatic increase. So the company can answer in this way: if you're residing in a smaller city than London and you would have been responsible for 3 fewer car accidents in the last 5 years, your class of risk would have been low. So this is a counterfactual example. So if A, B, C, D happened, then the class would have changed from high to low. Or you also have a semi-factual explanation, which is an even if type of explanation. Even if you would be married and living in a smaller city than London, your class of risk would still be high. So we have some variations on some features, in the case of marital status and residence, which does not change the prediction. Okay, these are the two types, and not even the semi-factual, because the semi-factual, I think, can be evaluated in a similar way to counterfactuals. We're talking about counterfactuals and feature attribution, which are, like, I think they compose 95% of the.
These are counterfactual.
Counterfactual to the left, semi-factual to the right. So counterfactual is something, some small prediction that changes, some small perturbation that changes the prediction. Semi-factual is like a large perturbation that doesn't change the prediction. Other questions? Maybe from home? No one saying anything. Sure. Okay, good. So I think it's the final information before we start delving into the proper techniques. The differentiation between local and global explanation. So if you remember before, when I'm talking about feature attribution, I was saying something that there is like a generic rule that is valid for all data points. That is a global explanation. And I'm cheating a bit because this is more an interpretation than an explanation, but like the linear regression formula is a global explanation because I know that for any data point in the real line, an increase of 1 in X will correspond in an increase of M in Y. Instead, in neural networks, we usually resort to local explanations, which means I want to explain one specific data point, a prediction on one data point, or maybe its neighborhood. So since I know that the global rule is often very complicated, very complex, I need to resort to explaining something on a neighborhood or a point, and maybe hoping that on the neighborhood of the point, the function the model learns is smooth enough so that I can maybe approximate it with some linear models or some explainable, interpretable models. Then I also have this concept of local, which is a very common term, very new terminology, which is something between global and local. So you might be tempted to get a global rule from an ensemble of local rules. This is doable, but it's not really global because it can only tell you something on the manifold of your data and not something that happens outside of the data space. And there's a lot of techniques which work on basically putting together local explanations which provide some local, or let's say global explanations up to a certain degree of variation. Okay, good. So let's see what time it is. So it is 3:15. I think we can take a small 5-minute break before we go on to the next part and recover a bit the energies. I hope maybe there's still a bit more tea downstairs. So yeah. Good. See you at 3:20 something. Yeah. Good. Or maybe we can just take a picture with that here. Yeah. Yeah, we just started with a break. Bam. Yeah, exactly. Okay, good, perfect. Yeah.
Okay.
Is there still a task perhaps?
Yeah.
Okay. Yeah.
I need cheaper, but I don't know where.
Yeah. Usually we do like more breaks.
Okay, yeah.
Question,
Is a question here?
Leonor, are you, yes, please.
Hi.
Hi.
Sorry, yeah, I didn't want to interrupt, but yeah, I have a question for Professor Zullich. I was actually I was reading yesterday. It's a bit of a aparté, but the paper that you wrote about uncertainty quantification and how uncertainty in the input propagates to the output. I think it's a paper from last year because you also gave an uncertainty quantification focused workshop, right, at the AIDA summer school. And I was wondering if you have slides related to that, or if there is because I'm seeing that this is being recorded. So I'm wondering, did you discuss that paper at the last workshop? Is there additional material that I could consult? Because I'm very interested in that. I have now a situation where I have kind of a decision-based system, quite a simple decision-based system, but then the input comes from a computer vision system, which of course, has a degree of uncertainty that I want to be able to propagate through the system. And I was wondering if there's more material I could consult. It's a bit of a deviation from. I'm also very interested in today's topic, but yeah.
So for that, so the papers that I have on uncertaintification, they're done with Matias Valdenegro,
Yes.
who wasn't like the main reference for this course. I would have to talk about it with him because we do have a couple of presentations from, of course, when we presented the papers, which have not been recorded, so we only have the slides for it. But I'm actually quite sure that if you send us an email, I don't know if you have the email of Matthias, otherwise you can.
I can find it. I think I found both of your emails. He's also in Groningen, right? I think I found his website. Yeah. Yeah. I found his website. So that's fine. Okay. Yeah.
If you send us an email, we will be more than happy maybe to have a meeting with you and to explain your doubts. Yeah, good.
Thanks a lot. Yeah, thanks. And I was also wondering, are we going to be discussing counterfactual explanations more today for neural networks? Because that's a topic I don't know a lot about and I'm very curious about. Is that also in today's program?
So we will not be discussing about the specific techniques for generating counterfactual explanations, although there's going to be a mention about one of these techniques. But we will maybe concentrate later on which are the qualities that make good counterfactual explanations, and which are actually embedded in the way you generate the explanation. So it is the difference between like feature attribution and counterfactual explanations. In counterfactual explanations, you have this quality already present in the generation function, but for feature attribution, you don't check this and you just have some heuristics. So yeah,
I'm looking forward to it.
I think in about 1 hour.
Okay, fantastic. Thank you so much.
Okay. We're gonna go grab some water downstairs because here's this really little water.
We'll be back in maybe 3-4
Yeah, 3 minutes. And still recording? Okay, good. Yep. Okay, so after this short break, we're back. And as promised before, now we're going to go through some techniques for feature acquisition. First of all, okay, perfect. So, quick recap of what we saw in this previous hour. So, explanation is a token of human understandable information. We can use them for model debugging, regulations, or generically inferential considerations of a model. We saw feature importance, counterfactual explanations, and we also saw the difference between local explanations, concentrating on one single point, and global explanations, like rules that are valid for the whole model. Good. So the first technique I'm going to talk about today is SHAP. Who knows SHAP already? 1, 2, 3. Okay, good. So SHAP is possibly the most theoretically founded technique for feature attribution. And it is actually derived from game theory, in which we have some participants to a game that form coalitions, and you want to understand which is the individual contribution of each participant in the coalitions. So if we abstract from like the generic participant, we can think about a feature in a model being a participant to a coalition. So we form coalition of variables, and we calculate how much the addition, the presence or non-presence of the variable in any possible coalition contribute to the final prediction. So there's going to be an example. I'm going to do it like it's a kind of an interactive example of that. So let's suppose we have 4 participants or 4 variables, A, B, C, and D. And I ask you which are all the possible coalitions or all the possible combinations of A, B, C, and D. So let's see if we have some contributions here. So how can I combine A, B, C, and D in all the possible coalitions? So how can I combine these 4 participants into creating coalitions or teams of any size? No, but be careful. It's not a permutation because if the order of the variable in a machine learning model shouldn't be important. So it's order invariant. So if I say AB is the same as BA. Yeah.
Can I participate?
Yeah, of course.
Okay, so if we get it syncing, then it's 2 to the power 4. First, we can either use or not use A.
Yeah.
We can use or not use B. So 2 times 2 times 2 times.
Yeah. So I mean, we just create them. We don't know how many there are. You can like obtain it later. But we know that with one participant, we can form 4 coalitions, A, B, C, and D. Then we can go on with more participants. So who wants to contribute? 2 participants?
You can just state combinations.
Yeah.
A, B, a team,
Yeah.
B, C, A, D,
Yeah.
B, C, B, D, C, D. And then the 3.
Yeah, exactly. So we have A, B, C, B, C, D, A, C, D, and A, B, D. I think that's all. Yeah. And then we have, of course, A, B, C, D. Are we done? Yeah.
There might be the empty.
Yeah, the empty coalition, which is also important because this empty coalition forms the baseline that we compare the predictions. So the way that SHAP works is doesn't only give a value or a coefficient of importance to each of the variables, but it defines them with respect to a baseline. So the meaning is how much that single variable contributes with respect to the baseline, which is the empty coalition. How do we simulate the absence of variables? Well, in linear models, you can just retrain the linear model without a single variable because we know that the solution is deterministic. There's no stochastic gradient descent in linear modeling. We always use the ordinary square rule, which is deterministic. But for a neural network, it might be very inconvenient to take away a variable and retrain the neural network. So what we do is simply consider the average value of these predictions. So for example, we have A, B, C, D, we train the neural network with it to create these like three-way coalitions. We just say, okay, A, B, and C, I take them from the data set, and D is the average value of D in the data set. So we simulate the absence of a variable in that case. Or if you have images, for instance, you can do even better because you have notions of like neutral tokens, neutral pixels. They could be, for example, fully white pixel, a fully black pixel, or a gray pixel, depending on the problem. So we must find a way to simulate the absence of one or more variables, and usually that is averaging or occlusion, we can call it. And then once we have calculated essentially the prediction on all of these coalitions, so that would be 4, 10, 14, 15, and 16. So we have to basically run 16 predictions for just getting the feature importance. We can combine them in this way. This looks like a very threatening formula, but it is not. So essentially the concept is I take the prediction of one coalition, which includes the variable j, and I subtract to it the prediction on the same coalition without the variable j. And I iterate it through all the possible coalitions in my set of features. And this W of S, it's a weighting term. So it's a weighted average of all of the predictions in my coalitions, the coalitions that I found. What's in weighting? It's a very complex formula which involves basically it's a ratio of factorials essentially, which includes the number of all possible features, combination of all possible features, and the number, a subset of coalitions which include the feature that you're studying. Yep.
Why aren't all of the terms equal? They need to be weighted sound.
Because
isn't every feature equal?
Yeah, in this case, it depends on this, and basically it's dependent on the relative size of a coalition with respect to the whole number of features. So this is why you don't give the same weights to all of the possible coalitions. Okay, so I think this is all. Do you have other questions on chat? Okay, good. Yeah, please.
Really issue that all features exist on also.
Yeah, exactly. And also not only that, but in this case, we're also, since we're providing like a single value to each feature, we are also considering basically that all the features are orthogonal, which is not very often not the case. Yeah. Because for example, by occluding feature D to create this coalition, it might happen that also the values of A, B, and C change in the data set because they are correlated with each other. This is the case of multilinearity. Exactly. And this is already one issue with chat, which is present in almost all other feature attribution techniques, that you want to provide one single value per feature, but you don't consider the feature they interact with each other. Okay, so here we have an example, again, with the California housing data set. So I have these variables with a given value, and I have a specific prediction. Notice that we have negative values because all the features have been standardized. So they are distributed as a normal with standard deviation 1 and mean 0. And this is the output of SHA. So for this specific prediction, notice this is a local rule. It's not global. So I cannot say that longitude is the most important feature everywhere in the data. It is only for this specific instance. So longitude provides an increase of 0.57 in the overall prediction, which is in $100,000. So we could say that longitude has a contribution, an average contribution of $50,000 in determining the prediction, which doesn't mean that if I take away longitude from the data, then the prediction decreases by $57,000. That is the average contribution in all the possible coalitions. So I'm not explaining this case right here, where D could be the longitude, for instance. I'm explaining all the possible coalitions where D is not present, which means these three, these two, this one, and this one. So on average, longitude contributes $50,000. Notice the contribution can also be negative. The latitude is also a very important variable. It doesn't mean that since it's negative, it's less important. It is very important, but it has a negative contribution. So the higher the latitude, the lower the house price. It's an inverse relationship. Median income is also important, etc., till I reach population and average number of rooms, which is borderline 0. Questions? Okay. Let's go on. So now we have seen SHAP. There are several other techniques for providing explanations. SHAP is model agnostic, which means that I can apply to any type of machine learning model, because I can do like the feature removal in any model. Now we're shifting our attention to model-specific explanations, and specifically we're talking about gradient-based methods for convolution for neural network, and specifically we'll see examples of convolutional neural networks. So the first explanation that I'm going to talk about is the gradients, also called vanilla gradients or vanilla backpropagation. And this is like the very basic functioning of a neural network. Backpropagation is the basic tool that we use for training a model, for determining the gradients for training a model. So what I can do, normally here I have like a loss function, which takes like these values over here, aggregates them with a function g, and then I have the backpropagation, here is the loss function, and I backpropagate the losses. Here instead, let me erase this. Okay. Here instead, what I do is I take one of these output neurons value, for instance, the one associated to the class dog, and I backpropagate this. I can do it because it is a single scalar. To do the backpropagation, I just need a single scalar, and which has been obtained from the model in a differentiable way. And I can do the backpropagation, and instead of backpropagating on the model weights, which would be indicated with the theta, instead I go even more backwards, and I backpropagate them on the input data x, which is something that I don't normally do. Because normally I stop in the weights because I want to update the weights. Here I shift my attention from the weights, which are fixed, to the image. And I want to ask myself, which are the pixels that are more sensitive, provide more sensitivity in determining this given output for the class dog. So by doing that, I obtain this sort of a saliency map like this. So each pixel has a scalar value, which is normalized between 0 and 1. So I can plot it, and I can find also ways to overlay it on top of the original image. So here what I see is a very noisy map in which the dog is highlighted, but also actually the cat is highlighted. So this with a gradient backpropagation was one of the first explainability techniques for deep neural networks, but it's very fallible, as you can see. It is not really considering the features only of the dog, but is also very sensitive generically to noise in the whole of the image. And sometimes you can also take the gradient and multiply times the input to give also a more granular and sensible explanation. But both of these techniques are not really that good for class discriminative features. So this gives you generic features the model is looking at, but not specifically those that are important for the class dog or the class cat or class fish. Questions? Yeah.
If you have a regression model
Yeah.
and not a figure, can you say for every prediction what are the dominant features that led?
Of course, yeah. So images, the reason why you use images a lot is because you can visualize everything very easily, but nothing prohibits you from having like a tabular data here. So you have like 6, 7 features. You have one value of gradient for each of the features. This value can be positive and can be negative. Positive means it contributes positively to the prediction. Negative means it contributes negatively to the prediction. No problem. Other questions? No? Good. Then we go to integrated gradients, which is a technique which is still used a lot. It's an evolution of the vanilla backpropagation. So instead of having one single data point X, which I had before, I generate an array of data points by interpolating between X and X0, where X0 is like a reference baseline. You can think of it either as like an average data point, or for images, a completely white or a completely black image, as in this case right here. So I start with an original image, and I have a black baseline, and this is a linear interpolation in 5 steps between the original image and the black baseline, guided by a value alpha. So 0 is the original image, 1 is the baseline. And this formula also looks very scary, but it's not scary at all. You have an integral over alpha, which resolves in a finite sum, essentially, on real-life data, because I cannot have infinite values between 0 and 1. So it just tells you that this is an average of the gradients, of the feature map to be generated with the gradients. So these are the examples of the saliency maps for these 5 images. With integrated gradients, basically you average them in that. And of course, notice that it's still not perfect because this is classified as human. And of course, you have human characteristics here, but also the sun is contributed a bit to the prediction, at least according to this tool.
But this, I think it's because the blurring, or how you say darkening, centered around like some states.
Yeah, exactly.
And it affects
Exactly.
because there's nothing else.
Yeah. There's a possible explanation, absolutely. But generically, these like raw gradients-based tools are very sensitive to high frequency patterns. So the sun is very light, so it's a high frequency pattern. Yes?
I didn't get what does this tell us? I mean, you have many perturbed versions of the same data point. How do we actually use them to evaluate our, to interpret our results better?
Yeah, exactly. So there are 2 points. First one is you see here in the previous slide how noisy this explanation is, and integrated gradients gets rid of a lot of the noise. You can see also here how noisy like these 3 are and how clean this actually is. It's like clearly concentrating on the human and the sun. But here is a huge blob of point around the person that is climbing.
So you negate the effect of the feature that should not be contributing.
Yeah, exactly. And the second point, which is something that we'll be discussing later, it is a more robust explanation, which means that small perturbations of the image will essentially lead to the same explanation. While other techniques, if you add perturbations, they will produce wildly different explanation, which is counterintuitive. So now we can have the evolution, essentially, of the vanilla gradient, which is the technique which is used the most on image data and also on other types of data, which is GraphQL. So this is slightly more complex, so I'm going to go through it step by step. So you have your model, which produces a feature map as output. Normally, after the feature map, you have a flattening, which can be achieved by just flattening an array, or you have the global average pooling. This is like the technique is oblivious to the specific flattening techniques that you use, and then you have a prediction step. So just one more step than before we consider a neural network as the whole of this. Here we highlight the last convolutional layer, reproduces a feature map in 3 dimensions, this AL. And what I do, I take, as before, the neuron for the dog class, and I backpropagate the gradients, but I don't do it until the very first image, but I stop at the feature map, AL. I stop here. So, the reason why I stop here is because essentially by assumption on how the convolutional neural networks work, they learn hierarchies of features, and the closer I am to the input, the more these features are very simple, like orientation, color, and the more the more closer I to the input, the more dependent on the input they are. Instead, this layer here, which stands at the end of the hierarchies, learns semantically meaningful content. So I hope that by stopping the gradient here, the gradient refers only to the class dog from which it is generated. So I'm hoping to get rid of all the noise that I had before in the vanilla saliency map. But I'm not stopping here with respect to the computation of the feature map, because I'm also combining it with the activation. So I have the gradients, which have the same shape as the activation, so still these 3-dimensional maps. And what I do with this very complex formula, which is actually very simple, it's a simple average. I average according to the spatial dimension. So here, what was height and width gets reduced to a single scalar. And I do it for all the channels. Usually these channels are 512 or 1024. So I reduce a 3-dimensional content to a vector of scalars here. And this tells me, essentially, according to gradients, how important each channel is. And then I combine the gradients with the activations. So this is the combination. It's the element by element multiplication. So this is to distinguish it from the matrix product. This is not a matrix product, it's a scalar product. And so essentially what I do here, I combine this multiplied by this multiplied by this, etc., etc. And I use the ReLU function for a very simple reason, is that like the negative contributions are telling me what is going against the class dog towards all of the other classes. So it's not really that helpful for me to know something that is not connected to dog, but to all the other classes in my data. If I only have 2 classes, then it makes sense to retain the negative contributions, because I know that what is not dog is going to lead to cat, for example. But since I have other classes, that information is not really meaningful. It's a very heuristical approach. So the ReLU is deactivating all the negative contributions, and I remain only with positive contributions. And this is a matrix, essentially. Averaging according to the channels. So I go from something which is H times W times M to something which is H times W. So I collapsed all of the channels into one single matrix. And now I'm almost ready. So this is an attribution map, and it gives me pixel level attribution. But the problem is that normally the image is much bigger than this one. This can be, for example, 224 times 224. And in the original paper for GradCamp, this was 7 times 7. How can I produce like this very beautiful overlay of the attribution map with respect to the image? Interpolation, yeah, very good. So I run an interpolation, which is usually non-neural based. I don't create another neural network interpolation, but I can use like regular techniques like bilinear bicubic interpolation, nearest neighbor interpolation. It's all computer vision stuff which can be run in milliseconds instead of like the prediction of a neural network. And this is the last step. So I combine essentially information for the gradients, information from the activations, and I generate the final explanation with this interpolation step. Clear? Questions? Okay, good. Of course, I'm talking about images, but I can use it for any type of data and also for text data. So in text data, we can have this question, welcome back, ladies and gentlemen, the next token. So what I do here for generating the prediction, I have an extra step because I have to produce the embeddings. These are one-hot encodings, representing one-hot encodings in a dictionary. So I need to project them to a dense two-dimensional space before I can actually run the prediction, for example, by a transformer. For a single prediction step, again, I have a probability distribution. I pick, for example, the most probable value, which is gentleman. And to attribute the gentleman, so what is important in the attribution, I can run again backpropagation. So again, I go from this output for essentially backpropagate into these 4 inputs, and I get 4 gradients that all live in a q-dimensional space. So now I have a problem in the sense that this is a unitary concept, and this instead lives in a q-dimensional space. So how can I aggregate all of this to produce a scalar value of importance for welcome? It's simpler than you can think of. Dividing by what? Don't worry. Yeah.
I'm thinking of thinking it like going from every word token into the two-dimensional space.
Yeah.
Calculate the distance, for example, between distance or something like that. And then working this way. So not going from the two dimensions back to the
So what you're saying makes sense, but that is a bit more advanced. It's known as a contrastive explanation. So you're trying to get what attributes this and not that when you're taking distances, for instance. But in this case, I really want to go from the q dimensions to one scalar, and I can take a lot of things. I can do mean, maximum. I can take the minimum, whatever. If the minimum could be, for example, if I want to get a negative value of attribution. So I can take the mean for all of the dimension of the embeddings, or the maximum in all the dimension of the embeddings, and get a value for welcome. Okay. So I remain with something like this, where ladies and end are the 2 most important tokens. And welcome is also kind of important. And of course, here from before, you can already see that with the images, with image classification, what you expect of an explanation makes more sense than in text-based data.
Do we have to nature generation? It's not over and
it depends on the type of data that you have, because we saw it previously. Let me go back by a few slides. And here, you can see that in this case, think is actually more led by innovate. This is still a transformer. It's like a smaller transformer in this case. So it's not
the transformer space in place. It will go with the ISO.
Yeah, of course. This is another this is another model. This makes sense when you have transformers, because transformers look at all the past tokens, not only to the last one. So yeah, in LSTM, I don't know what you can do. I actually never thought about explainability for transformer or LSTMs. No, but they make sense when you have a few data. Yeah, and also for like smaller dimensional data, they make a lot of. They make a lot of sense for text because you have a lot of data and you have a lot of dimensions in the data. But for smaller problems, when you don't have a lot of data, then STM is still very good. Okay. Now we can talk about the contrastive type of feature importance. So contrastive is what I was introducing before, is attribution towards output A and not output B. So I'm trying to find the features that are specific for one class and not the other. And this is also a very important example, especially if you need to provide specific explanations for why high risk and not low risk, for instance. So this is a picture from a recent paper that introduces FinerCam, which is a contrastive version of RadCam, which we saw before. So the question is, what is the difference essentially from blue grosbeak to Grandala, which are two birds? And actually the model, if you see here, I don't know if it's very evident from the monitor here, but you can see that here you have one explanation for blue grosbeak, which is very widespread, and one explanation for Grandala, which is also quite big, and they're kind of overlapping with each other. But here you can see that when you ask the model, what is the difference between grosbeak and Grandala, you only have this version, this feature over here, which is related to the color of the wings, and also a bit on the top of the skull, which makes sense because you can see here that the skull is very flat for the blue grosbeak, and it's very rounded for Grandala. So the way you achieve this is actually just a very simple modification to RadCam, because instead of taking the gradient of one single output, you take a gradient of a difference between two outputs. So in this case, I can explain, for example, what is the difference between dog and cat? So why are you model predicting dog and not cat? So you only get dog-like features, because in the end, if you think about like the shape of the animal, dog and cats, they do have some similarities. They do have a common ancestor. And the similarities can actually mislead the interpretation of an explanation. Because you might think that the model looks at specific features for the cat, well, these features are actually shared with dogs. In this case, you get rid of all the dog-like features, and you only get what makes a cat a cat. Okay, so now we can have a bit of a recap for the explainable AI part, because we are ready to start with the evaluation part. So again, an explanation is a human understandable information. Interpretability is a property of the model. Explainability is referring to the usage of external tools after a prediction has been run. Feature attribution aims to rank features in the context of a prediction and gives a saliency score to each of the features. We saw SHAP, which is a game theory-based approach in which you form coalitions of the variables and trace the individual contribution of each variable. We saw GradCam and gradient-based methods for images. In GradCam, you fix a hidden layer, match gradients with activations, and upscale on the original image. And also we saw FinerCam, which is a contrastive version of GradCam. Of course, there's a lot of other explanation tools that we haven't seen. Examples of line, layer-wise relevant propagation, deep list. Of course, if we had more time, we could look into that, but we need to concentrate now on the assessment part. So I suggest you, if you're interested, that you go more in depth into that on your own. You will see some very important references, according to me, at the end of the presentation that you can use to study more for XAI. So now I had a 15 minutes break, but I don't think it makes a lot of sense to do one, because we're gonna have a break soon in like 30 minutes, isn't it? Yeah. So I need just very quickly because I had I think we can go on with this part before the break, and
Can I ask you?
Of course.
What are the limitations of this?
We're gonna see some of them now.
They don't work.
Yeah, exactly. There are several limitations. Specifically, I can concentrate on GradCam also for a second. So the GradCam is a heuristic-based approach. So it doesn't have any theoretical validation like SHAP has instead. So in GradCam you do well, besides the absence of visual interaction that we already discussed before, you do have an important limitation, which is related to this interpolation that you go back to the slide.
You need to share it in those things.
From here.
Also, like that.
I think it got done on its own.
I'm sharing your screen.
Yeah, I think I'm sharing it. Yeah. Yeah.
No, you're not. Well, not with us at least.
Oh.
Yeah, you were until the 15-minute break slide.
Okay. I don't know why. Yeah, because okay. Yes. I think because I closed the presentation, so the sharing got blocked. Okay, good. Sorry about that. So you see this process of interpolation that you do. So this has a strong assumption, because if we go back to this slide over here, you're actually saying that the pixels that are present, for example, and let me change the color of my pen now so it becomes evident. So the pixels that are present here are somehow spatially connected to this area of the image. Because if you do the interpolation, you're overlaying some information that comes from the final layer to the initial layer 0, which is the input. But this is very heuristical. There's nothing that says that, because if you have like, for example, 50 layers in between the image and the activation map, this neuron, it sees the whole of the image. And there's a concept that I don't remember the name of right now, which is connected to how bigger of a portion of the data each layer sees. But in convolutional neural networks, since your convolution kernel is small, the next layer sees only a small portion of the data. But if you go more and on and on and on, the receptive field becomes bigger and bigger. So it is probable that features present in this side of the image can actually affect this portion of the feature map. So by saying that what I see here, the important score that I see here is related to this area of the image is an assumption, which can mislead. Sorry?
Like if it's like the assumption is that if left out, has sometimes then it will be also left out.
Yeah, exactly. In very simple words, what is top left in an image is gonna be reflected in the top left area of the activation, which is apparently true to a certain degree because GradCam works.
Yes, that's what I.
But it's not necessarily. There's no theoretical rule that says that. Yep.
Are there any checks to see if either application-wise this is true or not? Validated.
Yes, we'll see some of them later. It's related to the concept of faithfulness, this one. So you can see if actually the model is GradCam is telling you that important features are actually important for the model. Other questions? Oh, yeah, of course. So,
Yeah, saying thanks. Yeah, so I was wondering, someone had a question about the LSTM, and I was wondering sort of more broadly if you know, because I've worked on tabular data and imaging data a little bit with explainability methods, but time series data, I don't know where to start. So I don't know if you have a paper to recommend or a Python workflow to recommend, or
Yes, I do have a paper to recommend. It's going to appear later during the next slides. And generically for time series data, I suggest, maybe I can type it in the chat very quickly. I suggest one professor, I think she's at Oxford or Cambridge. Here, it's Michaela von der Schaar. Oops, and she is, I think she started with computer science or statistics. Now she works in a huge lab where they do XI for medicine, for healthcare.
Yeah.
And she has a lot of paper on trying to explain time series data. And we'll see one which is like introduces a technique called Dynamask.
Dynamask. Okay, cool. Thanks a lot. Yeah, I know her name, and indeed I associate her to the biomedical world, but I didn't know she did time series stuff as well. Cool.
Yeah, she
Thanks.
has time series stuff. Yeah, definitely.
Yeah. Thank you.
The last part, Michaela.
Van der Schaar. Schaar. Let's go back.
Okay, I got it.
Okay, but you will see she's in the reference. So yeah, it's in one of the like important papers that I indicated. Okay, good. So let's go to the next part. Okay. So I will skip this introduction because we didn't have any break. But you will ask yourself, we haven't discussed of one specific type of explanation introduced before. And which one? It's one that also you had some questions on. So we've seen, okay, feature attribution. But what about counterfactual explanations? Exactly. We haven't discussed about counterfactual explanation. Why? Because counterfactual explanations actually now we're shifting towards the evolution of the quality. Counterfactual explanations, counterfactual examples have this notion of like quality metrics embedded within the methods to generate them. So, on a very simple and general level, counterfactual explanations are just an epsilon generated by an epsilon perturbation under some conditions. So I have the original data X here, and I generate an example X prime by adding perturbation epsilon. So the first idea is that f of x, the prediction for f of x or f of x prime in this case, has to change significantly. And this is an example which you can on how you can generate counterfactual examples in regression settings. So instead of saying I want to change the class, I want to define, for example, a delta value so that the prediction is bigger than delta. So I want to have like a change of prediction which is substantial. So I say, okay, let's change, for example, the predicted house price by $10,000. So I don't want like a small perturbation which causes a small change in output. I want a small perturbation which causes a big change in output. So that is one possible way. And epsilon is small enough. So small perturbation, big change.
But to quantify what is small and what is big,
yeah,
you have to do it by yourself.
It's task dependent. And normally, for example, if you're working in XI in medicine, for instance, you might want to talk to the doctors and see what they expect for a big change in prediction.
Also, you go with normalized values.
Yeah.
To have plus or minus 10% to it. So
yeah, exactly. You can do something like that. Exactly.
In terms of learning, doesn't matter that much. Actually, how we generate by diffusion now. We economically generate image. So we know that the term is right.
Yeah, but diffusion models are quite different from classification models because it's like a inverse diffusion process in which step by step you remove like a slight amount of noise until you recover the original image in the training data.
No, my question is that deriving from the mindset of diffusion models,
yeah,
I think epsilon being small enough or big enough doesn't matter that much.
I mean, it matters not for the model itself, but it matters in generating a data point which is close to the original one. Because, of course, you can always find a big perturbation that changes the model. You can always say, okay, if you're a woman, 32 years old, living in London, if you were a male, 75-year-old, and you lived in Aberdeen, for instance, that doesn't make any sense from a communication perspective. You always have to think of that the explanation is not for the machine, the explanation is for people. So predictions are for machines, explanations are for people. So you want to, if you want to communicate something using the counterfactual explanations, you want that the data is kind of similar, so that you can have a serviceable explanation. So we saw before, basically the goal is to answer the following sentence. If A, B, C would have changed, the prediction will be substantially different. Or for classification, if A, B, C would have changed, the predicted class would have been Z instead of Y. Yes?
I'm thinking about it, and how do we interpret the results? Meaning, I see that a perturbation in one feature has or has not an effect on the prediction. Does this mean that I can drop this feature, or that this feature is important, I need to keep it?
That is the big difference between that is a very important observation, is the big difference between counterfactual explanations and feature importance. Counterfactual explanation is not meant to identify important features. That is the thing. Counterfactual explanation is meant to basically find a set of features that change the prediction on one single case. So it's more of a philosophical difference, because I think that if you generate enough counterfactual explanations, you can also have ideas on which are important features, but the goal is different.
Usually good data point wise.
Yeah, but these are only local. They can never be global counterfactual explanations. Yeah. Okay, so let's recover the example of Susan from before. 32 years old, lives in London, single, pre-car accident in the last 5 years. And she had an increase in premium because she was deemed as a high-risk customer. And now our company generates these 3 counterfactual examples that we want to communicate to Susan. So counterfactual examples usually are presented in terms of variation delta. So this is the variation with respect to the original data. Like here, there is no variation in sex. We have an increase of 7 years in age, change in residence, change in marital status, no change in accidents, and the new prediction, which is medium risk customer. Then we have explanation 2, in which you also have a change in sex, and the change in accidents goes to low risk customer, and example 3, which changes only the residence and the accidents in the previous year. And my question for you is, on a very intuitive level, which of the 3 explanations is better, and why do you think it is better? Why is it?
All changing normally.
It's changing 3.
Okay.
Age, residence, and marital status. Yeah.
I'd say the third one, because it has the least amount of changes.
Yeah.
So it is easy for you to extract conclusions.
That is an important observation. Usually we want our counterfactual explanations to have sparsity, which means that there's very few variables that actually change. But there's also other things that I might think of. Let's see if you might have some ideas. So one is sparsity, of course. And let's say that I add another explanation. Oh, you had some observations?
Perhaps we should not include in explanations things that the user cannot change.
Yeah, exactly. That is another important observation. This is called, I think it's agency. I don't remember, but we'll see it later. Let's say also this example. So here, this is the same explanation as number 3, but I have minus 27 accidents in the previous 5 years. Maybe this goes to low risk instead of medium risk. Is this 4 better than 3? Yeah.
I think no,
Yeah.
because it has a very rapid change.
Yeah.
So you cannot discretize between what is important and what is not.
Yeah. Exactly.
Let's say you have minus 10 accidents, so the same way you cannot tell.
There's a lot of difference between the original data point and the new data point that is being created. We have other observations also. So we have gathered some ideas. Before we go on to identifying which are the really important, qualities of a counterfactual example, I have another question for you. So let's say that we just take these two conditions that we had before. So original data plus epsilon equals the counterfactual example, with the conditions that f of x needs to change a lot and epsilon is small enough. Can you identify a similar type of perturbation? And this is tightly connected to trustworthy AI and AI safety, which is identical in definition to this definition that I gave of counterfactual example. There was a course on it yesterday, by the way. Yep.
Adversarial example.
Exactly. Adversarial examples, they have the same definition as this, essentially. So this is the original data point. This is like a small, imperceptible perturbation, which significantly changes the output. Adversarial examples, they have a different goal. Adversarial examples you don't care about finding something which is communicable, but it's just fooling the model. Also, this is basically fooling the model. But in counterfactuals, we're actually interested in providing something which is actually usable by the recipient of the explanation. So we saw similarity. The counterfactual example has to be similar to the original data point. We can quantify it in terms of distance between the original data point and the counterfactual example. Sparsity or minimality, and we saw also this. The perturbation should interest as few features as possible. And we can measure in terms of the so-called zero norm, which is not a proper norm, but the zero norm tells us how many features in the epsilon perturbation are different than zero. Plausibility, and this is also very important. The counterfactual example is plausible under the data distribution. If as an example, I have an 18-year-old customer, and the counterfactual example says, if you were 3 years younger, this is implausible, because you cannot drive a car if you are 15, for instance. And you measure it in terms of density within the data distribution. This is very hard to measure. And you have two properties which are not measurable, not quantifiable, which is actionability. The perturbation should include features which can be effectively acted upon. So here, if I ask Susan to change gender, that is a very drastic change. And it's not actionable. Or even like, oh, you should get married to have a lower, I mean, I don't think that like getting married to have a lower premium is like the main idea that people have with marriage. So yeah.
Mathematics doesn't care about.
Sorry?
Mathematics doesn't care about.
Exactly. That's why you cannot quantify that.
So do we not include them or do we still?
I think depends. Maybe you can use some large language model to automatically filter out explanations which are not good. But the idea is that you should generate multiple explanations and only provide to the user those that are actually actionable or are the most actionable.
But you still input them on the training, so you have to explain.
Yeah, you have to
So
explain.
you are kind of hiding something.
It depends on the goal. Because if you're a doctor and you have to communicate to your patients how I can decrease my risk of diabetes, it's useless that I tell you you could be a man or you could be a woman instead of a man. Yeah. But you could say you should you should be 20 kilograms less than 70 kilograms heavy, for instance. That is actionable because you can diet and decrease in weight. So your model has some features, but some features you can act upon, some others you cannot. And it depends on the goal that you have. So in some cases, actionability might not be a desirable property. You're right on it. And then we have like causality and discriminativeness, and the features contained in the example should have causal connections with the response, which you usually cannot find because machine learning is not causal, it just looks at correlations. And human experts should agree with it. And again, a machine learning model is not a human expert. So these three last properties, they should be enforced on a qualitative level. So just very quickly, how we can generate a counterfactual example? Well, this has been done in this work by Dandel et al. So basically, they have these four objectives: target level agreement, similarity, sparsity, and plausibility. Plausibility, you consider, is actually not it's not considered on the data distribution, which is very difficult to calculate. But instead, we take the distance between the counterfactual example and its nearest neighbor in the data space. So we want basically that for each of the features in the example, it is as close as possible to an existing data point. And we can do multi-objective optimization. And there's several ways of doing multi-objective optimization for optimizing all of these four requirements at the same time. And from this example right here, this is again an insurance-based, banking-based example. So you're asking for a loan, and this loan has like several characteristics. So there's a demographics, characteristic of the loan, so the amount, the duration, the purpose. And you can generate actually some examples on the probability of the loan getting accepted. In this case, the probability is 24%, so the loan is rejected. And these are examples in which the loan is actually accepted because the probability of acceptance is higher than 50%. Yeah.
I get that we need to check the mathematical, what can I say, constraints to create a counterfactual example, but we don't see limits. I mean, how similar should my example be? How sparse should it be? These are all case dependent, or you can find guidance in literature?
I think they're all case dependent, and I suggest that if someone else has done like XAI in your field, that you check in their papers what they actually do. Because
if you cannot find something similar, you just experiment yourself.
You experiment yourself, and I think you should include experts for the application that you're interested in to actually tell you, yeah, this is similar enough. Sometimes you have to use qualitative example in research. Unfortunately, in science, especially like deep learning, there's a lot of heuristics. So you just have to trust the expert, and the expert tell you, yeah, this is satisfactory, this is not. So in this case, you can see here that the objective, similarity, sparsity, and plausibility are actually indicated here. So you can rank the counterfactual examples according to three of these targets. And so I think we can skip like the considerations of these explanations. This is a very sparse, for example, explanation, skill and duration. So if you had a skilled job instead of an unskilled job, and the duration instead of 48 months would be 28 months, then your loan would be accepted. And you can actually say, yeah, I want a higher probability of acceptance. But in this case, you can see that the explanation is not actionable at all, because it requires you to have to be 30 years younger and to change sex and to have a skilled job and to have a small duration. So there's a lot of changes, and some of them are not actionable. Yep.
Shouldn't, if we take, for example, the first counterfactual skill, the minus 20 stuff, shouldn't every counterfactual that has these and more changes be also counterfactual or not?
Yeah, but you're interested only in showing those that have few changes, small changes.
Of course.
Also, there's another thing that I wanted to notice. This is kinda actionable. This is completely actionable in the sense that I can tell you, you should ask for a shorter loan in this case. And also another thing which is very important from an ethical perspective, you can see that sex is actually, we don't know if it's an important variable, but it's definitely a variable that comes into play in the prediction in Europe, this model will probably be illegal because you cannot discriminate on sex in the banking and insurance sector normally, at least not for cars. In Italy, we have there's very strong rules on that. So you cannot have, if you're, because it happens more and more that women get actually lower premia on the insurance until they made a law. No, you cannot discriminate for sex for car insurance, and also for a lot of other types of insurance, you cannot discriminate by sex. And I'm quite sure also in the bank you shouldn't. So also you have to be careful about what variables you include in the model. And also examples can leak biases that might damage your reputation as well. Okay, let's wrap up the counterfactual examples. Then we go on a break. Small perturbation, the significant channel perturbation. Usually they are producing the contents of categorization. So we steer towards the target prediction. And basically we want to consider closeness to regional data points, sparsity of the perturbation, plausibility, and actionability. Okay, so now we take actually a 30 minutes break, a bit more than that, 35. And when we come back, I would like you to create small groups, and people online can actually talk with each other. And if you're a solitary guy, you elucubrate alone on how you can actually evaluate feature attribution on what we have discussed until now. So now we have a long break. Let's take a tea, a coffee, a glass of water, and you can reason about it. We come back at 5, and we're going to start again at 5:05. So you have some time also to discuss between each other. Good. Okay, good. Still someone missing, I think.
No,
he left. Okay, good. So it's 5 o'clock, so perfectly sharp to resume with the lecture. Maybe we can also, should I close the door here so there's not a lot of noise coming from the outside? Yeah. Okay, good. So we had this break to also a bit think about how we can actually evaluate feature attribution. So the question is, provided you should have a saliency map generated with SHAP or breadcrumb or whatever, how can we evaluate on which axis, on which facets we can actually evaluate this feature attribution? So before, for counterfactual explanations, we saw, for example, closeness, sparsity, plausibility, and actionability. So how we can actually evaluate one saliency map? Yeah.
There are some papers that that you would have a ground truth on the attention map.
Yeah.
And then you would compute some sort of score with your breadcrumb or salience map.
Yeah.
And that would work.
Yeah.
Very in map recognition method.
So generically, we might have like a ground truth of what a saliency map might look at, and we can devise several strategies.
It's basically what I do in my work.
Yeah.
With map recognition, so I have a ground truth closure map.
Yeah.
And then I calculate similarity.
Yeah, you calculate the similarity. There are several metrics for similarity that you can use.
If someone
from Leonor, yeah, you can activate your microphone. You're muted now.
Sorry. Yeah, I mean, the notion of fidelity is often mentioned. I think it's a notion that was first mentioned in the Lime paper. And I think if I understand, I mean, for saliency maps, it would probably be a way of checking that is that if you give, if the model gives you a different prediction, it should give you a different explanation as well. And I think with vanilla saliency maps, what they observed is that that is actually not the case, that you often, the explanation depends more on the input image than it does on the prediction. And so that's one of the ways they concluded they weren't flawed. So fidelity to the model's predictions, well, decision-making process,
Yeah, so your explanation is on point. There are actually two different facets that are you indicated. One of them is like proper fidelity, also known as faithfulness. And this indicates the level of agreement essentially between the model and the saliency map. And the other is connected to the notion of robustness. So robustness can be several things. One of them is like if you have an explanation generated for one label, that should be different than an explanation for another label. The example that we had before with cat and dog, that you don't want the same features to be relevant for cat and for dog. Yeah, so I think we're covering almost all of what we're going to discuss in the next slides. Maybe you can come up with something more, which is more connected to the human understandability of the saliency map or the feature attribution. Let's see if we have some ideas.
Sparsity?
Yeah, that is also a possibility. Let's call it generically cognition. Sparsity is definitely something that you might want in some specific feature attribution techniques, like for example, in the case of tabular data. In the case of images, instead, sparsity is not always a necessary desiderata, in the sense that our visual cortex is able to process images very quickly. And so even if we have a lot of details, we're still able to grasp the complexity. But generically, we can group everything which is connected to cognition in a single category, which we will see later. Are there other questions on what we have said so far? Yeah.
Yes, I have a question about the robustness.
Yeah.
Do we refer to the robustness for the model decision or the robustness for the explanation?
It's a robustness on the explanation side. So robustness of the model is a generic property which is connected to trustworthiness of an AI. In this case, we really want the explanation to be robust with regards to specific perturbations, and we will see later what we mean for that. Okay, good. So how do we evaluate the quality of explanation? So let's talk about faithfulness, which is the first and probably most important of the characteristics, and also the one which is more often overlooked. So basically, this is how we grouped the categories from before, and this is based on this feature from research from Mike and Alta. We'll talk about it a bit later. She doesn't make it look so simple. So mine is like a simplification, which considers the fact that we are not actually evaluating other tools other than feature attribution in this case. But we have faithfulness, robustness, cognition, and coherence. Coherence is the alignment with the ground truth. So faithfulness is the level of agreement between the explanation and the predicted dynamics of the model. So how much does the feature attribution captures the decision-making process of the model? So I think that we can make it very easy with an example, as in this case. So we have an image and we generate a feature map, which is, sorry, an attribution map, which is indicated in blue. But we also suppose that we know which are the important characteristics for the model. So we suppose that we have full access to what the model considers is important. So only in we can say that only in two examples there is some degree of faithfulness between the model and the explanation. In this one, there's almost exact, like perfect faithfulness, in the sense that there's almost a perfect overlap between the two things that we are considering. Here, the XAI output is still faithful in the sense that it captures more of what the model considers is important, but at least the important pixels are part of the explanation. These are two cases in which there's perfect misalignment. In the first part, the explainable AI output is indicated something like the background, which is not really important for the model. And the second part instead is completely different. Is a situation in which the important pixels are in the background, and the XAI output actually indicates part of the bird as an important feature. And both examples can have very bad repercussions if we just take the output of the explainable AI tool as an oracle, which is something that should never be done. Because in the first case, we might get like a wrongful idea that the model is learning features that it is not actually considering. In the second case can be even worse in the sense that we have a false sense of security that the model is actually learning something correct, for example, to classify birds, looking at the head, while in reality, it's basing its decision off of noise or the background. And this last example can happen quite easily if you use, for example, saliency maps, like the gradient-based saliency map at the beginning of the second part, which react highly to high-frequency patterns. So this, like the head of the bird with a lot of like yellow colors can be high-frequency patterns, while the background isn't really that stimulating, maybe from a gradient perspective. So be careful, because this example is very dangerous, especially if you're in safety critical application, for example, medical AI. So basically, we want the explanation to include the most important features and the explanation not to include irrelevant features. So this is a bit of a stretch, like the second case up here, to say that it's actually a faithful explanation, because it includes a lot of irrelevant features. Yes?
But we are, to my perspective, we are doing all this stuff in order to understand which features are important and which are not. And
yeah,
okay, with the underlying physics, you might know a couple of them that are irrelevant, a couple of them that are important. Yeah. But what about the gray zone, the ones you don't know if they are important or not?
In this case, you don't know anything, because you're not matching something to a ground truth. Coherence is the level of alignment with respect to a ground truth. So let's say coherence is telling how much of the bird the explanation is containing, while faithfulness is how much the true important pixels according to the model align with respect to the explanation. And we never have actually access to which are the true important pixels, because we cannot access the black box fully.
So how do we do that?
Yeah, that's the what I'm going to explain you now. If it were easy, I wouldn't talk about it. Yeah. Okay, so how can you measure faithfulness? So we can start from a key observation, which is reliant on feature removal, which we saw before with Shab. So removing significant features should result in changing the prediction significantly. So if we remove features, like in this case, that are highly important, according to the explanation, we should see a substantial change in the prediction. Notice that I'm not talking about the ground truth. I'm not talking about accuracy. I'm talking about the prediction itself. So let's say this classification case, we have a clean image, which is predicted as church or with a 90% confidence. We generate our saliency map. We remove the most important pixels, and what we see is a decrease, is a drop in confidence. So we're not caring about ground truth. So there is no connection with respect to the label Y. It's just the outputs of the model. So we're just checking the Y hat. And so the idea is that there should be a connection between the importance level that we assign to the feature and the drop in confidence of the model. At least this is for accuracy. You can frame it in a different way for, this is for classification. You can frame it in a different way for regression. Like in regression, according to the positive or negative saliency of the region we remove, you should see a proportional change, positive or negative, according to the type of contribution in the prediction.
Their importance is usually defined as a numerical delta or
yeah, exactly. I don't think you can measure like a relative level of faithfulness, but you can measure it in an absolute way. And so maybe you can say, if you have like 3 different explanations, one is Shad, the other is line, the other is Gradcam, you can say maybe Gradcam is more faithful because the drop in accuracy, sorry, the drop in prediction is the highest one, for instance. So this leads to the technique or the series of techniques known as incremental deletion. And you also have the incremental insertion, which is the opposite. So in incremental deletion, what you have is basically you start removing pixels from either from the least important to the more important, or from the most important to the least important. There's not really a lot of change in what you in the way you do it, because in the end, the techniques for computing a numerical value out of it are similar. And basically, the idea is the one that we explained before. The more you remove the features, the lower the confidence should be, until at a certain point, basically the model should ideally have no preference for any class. So this like probability distribution should be completely flat when we remove all of the important features. So this is the key idea that you're basing yourself on. So how do you actually create a metric according to this? Well, you can use the confidence versus sensitivity curve. So we have 2 axes. Here you can plot the sensitivity, also known as the percentage of pixels removed. So you have percentage of pixel or of like generically features removed. Sorry? Like this. Here you remove like the top. Yeah. So this could be removed like the top 10%, top 20%, top 30%, until you remain with a black image. I'm still in the example of images, but this translates seamlessly also for other types of data. And here you check the model confidence in the first predicted class. So even if the prediction of the model changes, you always track the original predicted class. So this is always going to be the same one, even if at a certain point, one of the neurons has a higher, so the prediction changes. So one of the neurons, the output neurons, has a higher probability mass associated to it. Okay, and basically what you observe here, you want to observe a drop, something like this. So as you remove the least important feature, you observe like a small drop, and this has a sort of a non-linearity until you reach a certain point where, for example, this is like perfect flatness in the probability distribution. So this would be basically 1/k, where k is the number of classes. So this is the theoretical idea. In practice, it never works like this, because you might have multiple objects, or the features might be connected to multiple objects.
It's also dependent on initialization.
Not how you initialize the CNN, but the types of features that are learned will definitely affect the whole process. So the question for you is now, how do we go from a chart which is created from multiple values to a scalar? So how do we assign a value of faithfulness in this case? Do you have some ideas?
Yeah.
Sorry? Yeah, you can use area under the curve or area over the curve. That is something that's definitely done. So you either check for this or you check for this. And in this case, for example, a desiderata could be having a high area under the curve or a low area over the curve. Do you have some other ideas? So if I have two quantities that have to be kind of similar, so as I increase the other one, the other should also increase or decrease. Yeah.
Maybe a deviation from the gradient of y equals x. Gradient of 1, essentially.
Yeah, that is it's not currently used. It's not simple to implement that, and I have some ideas to kind of try to implement that. But it's something even simpler that you use a lot in basic statistics. So how do you measure the dependency between two? Sorry,
The covariance?
correlation, actually, yeah, exactly. Covariance is the correlation is the basically normalized covariance. So yeah. So you have correlation-based metrics. You can use Pearson's correlation. You can use you see that's a covariance term here, and you can use the Spearman correlation, which is the Pearson correlation on the ranks of the two distributions, on the rank of the confidence and the rank of the sensitivity. The Spearman correlation is better at capturing non-linear trends, like in this case. Or you can use, again, area under the curve, area over. As an example of the users, yes?
Yeah, you show us a typical behavior of the graph. I mean, the previous graph.
Yeah.
So here, wouldn't we expect a higher gradient for the first part where we exclude the most important features?
Yeah.
And then a lower gradient.
Yeah.
But yet we see a soft steepness at the start and the large one at the end.
Yeah.
Why does this happen?
This is because I formulated the problem a bit differently. So this actually removes the most important first. In this case, I removed the least important first. So you can see here.
Okay.
Exactly. Otherwise, it could create like an inconsistency in the access, because you start with you start basically from the opposite, and you would observe something instead like, let's change the color here. You would observe something like this.
Exactly.
Which is actually very equivalent as a problem. In this case, you would want a high area over the curve and a low area under the curve. Good observation. So IROF, which is one of the metrics which is used for this problem, is very similar to what I explained insofar. The only thing is that we do in addition is the superpixeling of the image, which means that instead of generating the feature map straight away and removing according to the importance of the feature map, which is very noisy, what I do before generating the feature map, I do superpixeling or segmentation, which is not a neural technique. So this is basically based on color properties of the image. So I identify area of contiguous or similar colors. This creates some discrete regions, and then I assign a saliency to each superpixel. So in this case, if the saliency map indicates that like this is the most important region, and I have a superpixeling that works like roughly like this, what I do is for each superpixel, I assign, for example, a value which is corresponding to the maximum of the saliency in this region. So in this case, I would take a value which is roughly corresponding to this area. And this makes the process much more stable, because we still have the notion that like small variation caused by the, for example, making some pixels gray or black can change the explanation a lot. In this other case, this is a device employed to make the explanation more stable. And then you do feature removal, and you calculate area under the curve or area over the curve, etc., etc. And this is one of the metrics that I used a lot, because it actually kind of makes a bit more sense than others. But all metrics that I have discussed so far, they have their problems. And I don't think we have 15 minutes of time. But maybe what we can do is we can try to work on identifying what makes these metrics not really that good. And I will recreate like one of the examples that we are checking here. And here we have sensitivity versus confidence. Yes.
I was thinking about something that might be troubling is, what about feature interaction?
Yeah.
What happens if a feature is important when another one is apparent, or the other way around?
That is a meta problem, which goes, it's a problem of the specific tool that we are using. So it's not a problem of the metric. but the tools don't capture feature interaction. So it's a problem that we will always have unless we change the formulation of the feature interaction method.
Okay.
So I want you to think about which issues might correlation have, for instance, and which issue might area under the curve and area over the curve have. And we can start maybe with considering this. So when is area over the curve equals to 0 or area under the curve equal to 1? Yeah.
If everything depends on one feature.
So area under the curve equal 1 is like when this area is like completely
So the last feature is the only one deciding.
exactly. Exactly, which means essentially what it means is that all of the features which are not important, don't have feature importance 1, they are all irrelevant actually. So I only care about the max of the importance, and this is actually not really true because it goes against the idea that I had before. The most important feature is the most its output, its impact in the prediction. If I have something which is 0.5 important, it should have still a relevant impact on the prediction. Instead, in this case, we are actually favoring very sharp explanations only, very polarized explanations.
I'm still criticizing this.
We are criticizing the metric for faithfulness. So area under the curve or area over the curve is not. We don't know about it, but you would like to have a gradient in the explanation. I mean, you might have situations in which you want to discretize or polarize an explanation, but in this case, if like each feature has a different level of importance in determining the prediction. And in this case, you're basically saying that only the most important pixel is actually represents an area of faithfulness, and the model doesn't look at anything else.
So you say that the method itself pushes the actual selection to be the steepest one, the one that depends on a single or a couple.
If we consider this metric for faithfulness, these would be faithful, the explanation that we would actually prefer, yes. And what about correlation? So I have one example here. So let's work in the assumption of linearity. So instead of having this like curve here, let's suppose that this would go down linearly. And so we can have like these points here. And this is, of course, a correlation of 1. What about this case instead? What is the correlation of this curve, of this line right here? It's also 1. You see that the correlation is insensitive to the slope. As long as I don't have a perfectly vertical or a perfectly horizontal line, the correlation is always 1, which means that even if the whole of the explanation includes only slightly relevant features, if I use correlation for measuring it, it's always going to be perfectly faithful, as long as these points are aligned. So correlation only measures how much we have like a deviation from the perfect line. So it's also not appropriate to use correlation because it doesn't tell us whether we have a situation in which, yes, this is faithful in the sense that it highlights some features that are important, but then we don't have the assumption that by completely removing pixels from the image, we should have basically a random prediction. So we cannot trust neither the correlation, neither the area under the curve or the area over the curve. Yeah.
Additionally, if I may, even the Spearman correlation does not completely include the nonlinear effect.
No, yeah.
Which is something important.
It includes nonlinear effect in the sense of monotonous
Yeah.
nonlinear. Yeah, of course. Otherwise, it's completely confused.
So
But
nonlinearity can be taken into account somehow or not?
yeah, because we still want monotonous, observe a monotonous curve.
Yeah, but what if your feature has a non-monotonous effect, non-linear effect, the result?
Well, in that case,
Which is usually physics through quadratics and sinusoidal.
yeah, but in this case, actually, that's what we would expect. That's what we want out of the explanation, actually. That the more important you remove, the more important features you remove, the bigger the effect you have on the prediction. So you want something which is monotonically decreasing in the sense of the confidence. Okay, we saw IROF and so proposals for improving these procedures. We had some consideration, for example, on the slope. So there are ideas. For example, ideas that you can have is doing some sort of curve fitting on, sorry, line fitting on a transformed version of a curve so that it becomes linear. So you have a linear regression whose coefficient indicates the level of slope. And you would like to have a steep coefficient, of course, in that case. Or another thing that you can do, like drawing upon uncertainty quantification. In uncertainty quantification, you have this notion, whereas if you take confidence and you take the accuracy of a model, for specific areas of confidence, and confidence refers again to the percentage, like to the probability mass that is assigned to the predicted class. You would like that highly confident predictions are highly accurate, and predictions with low confidence have low accuracy, so that you can have a similarity, like a one-to-one similarity between confidence and accuracy. So on average, a prediction which is 20% confident should be 20% accurate. And we can draw something similar. So we want to draw a dictionary, essentially. We want to draw a rule that says if the explanation says that this area is 50% important, removing that area and everything which is less important than that should have something connected to the 0.5 times impact on the prediction. And that is something that I plan to research. It could be a rule that you assign for what is faithfulness, because right now the notion of faithfulness is a bit undefined. You want that a number actually means something, and in this case, a number doesn't mean anything. You can only, if you use these metrics for predicting faithfulness, you only have some numbers that you can use to evaluate one method against the other. But it's not something that tells you this is 80% faithful, so it's okay. It's not like accuracy. You know, 80% accuracy is good depending on the problem. Do you have questions on this part? No. Okay. Good. So now we come to another issue connected to the computational faithfulness, which makes it very hard to compute with removal feature. And that is the connection to output distribution data. So do you know what output distribution data is? Sorry?
And the outliers.
Output distribution data. Yeah. So if I ask you what is output distribution data, what do you say? Not especially for that.
I would say it's so you assume a general distribution.
Yeah.
And then if some outliers are out of this distribution,
Yeah.
people then out of distribution.
Okay, so we are actually making a bit of conflation between what is an outlier and what is output distribution, but that is normal because normally it's two concepts that are a bit like thought of in a similar way. But an outlier is still part of the data distribution. It's just an outlier is a point whose distribution density is very low. So if we assume normality, for instance, we can have a data coming from the tail of the distribution is an outlier. So for example, it could be a person who is extremely short or a person who is extremely tall if you're considering height. Output distribution is something that doesn't matter at all with our data. So for instance, I train my model to recognize cats and dogs, and there is an image of a frog. So frog is not supposed to be in the data. Well, if it were a very weird looking cat, that would be in distribution.
But, okay, but as a model, I don't know that, so I will put it somewhere. Probably very, very random place, but.
It's very difficult to treat auto distribution data, especially with neural networks. So auto distribution is that the data point is outside of the distribution of the neural data, and which is different from outlier, which is an exceptional data point. This is an example of auto distribution data. The bird, in this case, it's something that shouldn't be evaluated by a model that has to recognize cats and dogs. So here I have like a short Colab tutorial. By the way, some of you can actually access it with this link, bit.ly/xi_faithfulness. Also, if you want to do it from home, here. So, oh yeah, can I see the screen because I need to reshare my screen. So we can do something. This. I have to go back to the Zoom, which is here, and share again. Let's share the entire screen. Okay, good. So here, I'm not going to run it because there's this Captum library, which is a library for explainable AI and explainable AI evaluation. It has some weird requirements, so it needs to reinstall basically everything in Google Colab, which takes quite some time, but the output is already there, and you can play around with it if you want from home. But this is just to show that I take a pre-trained model on Cypher10, which is one of the most famous image data benchmarks. It's outdated now. This is the model. This is the way I pre-process the data. This is an image. It's not super clear because the images are super small, but this is a cat which is biting the leg of a human, something like this. But the idea here is like the model recognizes this is correctly a cat. And what I can do is I can use guided GradCam, which is a variation of GradCam. There's like 20 variations of GradCam that you can use. And I generate the attribution, and this is the result, essentially. So we can see that the model mainly looks at like the back of the cat for the prediction. And there are some other important pixels here and there. This one is clearly not associated with the cat. So I run the prediction, and I can run the softmax to get the probability distribution. So this is the probability distribution, and we can see basically the model has perfect, almost perfect confidence on the class number 4, which is corresponding to the cat. As we can also see, not here, this is for another prediction. These are not the same values, but what we can see here we start removing pixels. Let's see if I also have a plot of what I'm doing here. Yes, okay, you can see that I'm removing features by basically here removing the features which have perfect attribution, in this case 1, then more and more until I remove the whole. Sorry, these are completely irrelevant features. For example, the model is apparently not looking at the head of the cat until I remove the whole of the image, basically. And here, what I see is that actually, from a certain point onwards, the model seems to behave very weirdly, in the sense that it's very wiggly, the probability associated to the cat. For example, at a certain point, with 60% of the pixel, the model is like 67% confident that it's actually a deer. And here, for instance, the predictive class is plain. 99% confidence. Yes?
From my experience, I don't have much experience, to be honest, with neural networks, but they're usually, if we take a random noise and pass it through the network, it usually is assigned to some particular classes, perhaps 1 or 2.
Exactly.
So perhaps this is what happened.
We can see that in this very famous paper from An Nguyen. And this is actually a art. It's exhibited somewhere in a museum. But these researchers, they produce with evolutionary computation patterns or random noise that neural networks classify with extremely high confidence. For example, the model believes it's a robin with 99% confidence. This is an electric guitar. This is a peacock. So this is a well-known issue with neural networks. The neural networks, because they are learned to reproduce one-hot encoded labels, they're almost always going to produce highly confident predictions, even when the input data makes no sense at all. So this is why we observe this behavior, that like at a certain point, the model is like really confident that this is a plane. And it's actually working against what we were thinking before, what we were thinking, our the rata, right? Like this nice curve, decreasing curve. So this is all over the place instead. And it's interesting that after a certain point, when few pixels remain, the model goes back to predicting that this is like a cat. Like in this case, almost, because like here is like halfway through a cat and a plane. Okay, and here you can also see that like we create completely random images, and some of them are predicted as again as a plane or a cat with high confidence. In some other cases, this is like the third one. What is it? It's a completely random image. This is 100% cat. So the problem is that by adding like these black patches, the model behaves in a completely unreliable way. So let's go back to the slides. And this means that if we really want to evaluate faithfulness in a faithful way, we have to have the model treat better auto-distribution data. And auto-distribution data, we mean specifically data with black patches. So how can we solve this problem? What can we do about it? Yes.
Perhaps a naive way would be to train the model with black patches.
Will you please send the code in the chat? Of course. So let me move here very quickly. This is bit.ly /xi _ Yes. And so how can we solve this issue? One idea is, yes, we can actually add black patches as like data augmentation stuff, the training. Other ideas, we can change feature occlusion, for example, with blurring. And we hope that the model is actually better at handling blurring. Or something which is also very interesting, and I know that there are some guys, I think they are in Dresden, but they are working with using generative models to do in-painting. So instead of removing the important features, you patch them with something generated by an AI. And this patch should include features which are not relevant to the class. So this is one idea. Oh, yes, please. Yeah, or you can unmute yourself.
Yeah, sorry. I was just wondering, what about the whole discussion about epistemic uncertainty and using that for OOD detection? Can that be used to inform these explainable AI metrics or not really?
Well, in this case, the concept is kind of similar in the sense that you want the predictive uncertainty to reflect the level of occlusion that you have in the pixel. So you should have more and more uncertainty as you remove features. So that's a concept similar to what we talk about in the quantification of uncertainty courses, in the sense that you would like the predictive uncertainty to be aligned with how actually like the model knows of the data, and clearly the model doesn't know what a completely black image is. So you need to train the model to actually recognize that.
Okay. Yeah.
So we're saying This is the first strategy. So just add random patches during training. Second strategy is actually addressed, sorry.
By adding these out of distribution cases to your training, do you need to introduce a new category as well? Where should the model categorize?
No, exactly. That is the problem in the sense that you only get rid of the completely out of like nonsensical predictions in that case when you have like random patches, but still it doesn't solve completely the issue because the model is still going to output highly confident predictions anyways. So the idea is another idea that I have for like a research is not only add like partial feature removal, but also incorporate explainable AI, some explainable AI technique very simple, like for example, gradient based, so that you remove according to the saliency. And if you remove a highly salient portion, you don't have like a one hot encoded label like this. But if you're patching during training, you should have like something like, for example, 0.1, 0.1, 0.1, 0.1, and 0.6, something like this. So that you forcibly tell the model that it should tune its accuracy depending on how important the features that you remove during training are. Because you need to have the model learn this behavior somehow. Otherwise, the model always learns to do this. And featuring painting, for example, could be this. But the idea is that instead of like, if you remove this portion of the image, instead of like regenerating a face, you would have like other features that should, it would look awful on faces, like really something otherworldly. But yeah, that is an idea that you can have in feature removal. Questions? Okay, let's look at the time. Yeah. So another idea also, which kind of seems to have more sense, is the explanation in the embedding space. So instead of running the explanation on the output layer, you want to run the explanation in the layer before the output one. So this is usually a highly dimensional layer in which each point has a specific semantic meaning. So the idea is you have like, let's suppose this is like a space in 2 dimensions, just to explain what I'm doing. And so you would have like a reference point, which could be, for example, the projection of the original data point. So let's call it g of x. And then x prime is the perturbed version after patching, and you have it somewhere else, like for example, here. So can we leverage this embedding space to actually generate explanations? And apparently this can be done. You can do it in several ways. For example, you can project all the data points of a specific class in a given area. You calculate, for example, the centroid of it, and you can compute some confidence by measuring how far the projection is to the class centroid. And we tried to generate an explanation, for example, by taking the difference between the projection of the data points and the centroid, and it seems to have some sense. So the idea here, if you want to measure faithfulness, you can say how like the distance with respect to the original data point, and this should go further and further. And this is what one of my thesis students that she graduated 2 days ago, what she did. She did a nice video. So this is ImageNet, which is a subset of ImageNet. It has only 10 classes. And so she took the example of the church that you saw before. And she trained a model using contrastive learning, which additionally produces better embeddings, better clustered embeddings. So this is a projection using Disney of a 32 or 64 dimensional space onto 2 dimensions. And you can see how the classes seem to cluster quite well. So she's considering the example of a church we saw before. And this is the projection. And you can see that the projection gets further and further as you patch more percent of the image. And this is actually the behavior that you should observe. And this is something which is actually observed in the literature for uncertain quantification, that if you use models which focus on the embeddings instead of the proper output, that they have better auto-distribution detection capabilities. So probably the key to measuring faithfulness lies in the embeddings and not in considering the output prediction. This is still a prediction of the image, and the embedding is still a prediction. It's just focusing your attention somewhere else in the model. So this is an idea that we will certainly continue to work on, and if you want to contribute, of course, let me know. Yeah.
I again question you about regression.
Yeah.
How would you see this work in regression problems? Because I cannot see it at the moment.
I think in regression it will work quite similarly, because I think that the meaning of the embedding space is still the same, in the sense that the embedding space captures captures semantics. So you should still be able to observe variations from the original data point by using metrics in the embedding dimension. Like, for example, the L2 norm. So in that case, it could be even like task independent.
Yeah, but in regression problems, you have essentially numerical predictions,
Yeah.
not absolute predictions
Yeah.
as classes.
Yeah.
So there shouldn't be different spaces where data
Yeah.
points are accumulated.
Of course, in the case of
rather a cloud of points
Yeah.
everywhere.
Yeah, exactly.
So you cannot extract the same conclusions.
I think
for
you can
regression.
you can still do clustering in the sense that you can run in this case we didn't run any clustering. This is like visualizing with the label, the colors of the labels. In that case, you can still run clustering. For example, you can still turn a numeric prediction into a categorical prediction by partitioning the prediction space. So for example, you have from 0 to 10, from 10 to 20, the same thing that you do with age, for instance, where you have an age number, but you can also categorize it in before 18, 18 to 25, 25 to 35, etc. So you can still observe differences in this way.
This requires a bit more trial and error for the
it's
boundaries of the different.
If you read the literature for explainable AI, like I would guess like 90% of it is on categorization, so on classification. So I think that if you do work on regression, there's like a lot of open research field that you can insert yourself quite easily. Yeah, no problem. So this is again the issue with the correlation that we had before. So you can see all of these lines have a correlation of 1, and that's why we cannot trust correlation. Again, consideration on area under the curve, which we discussed before, that it favors polarized explanations. Also, if you look at the literature for faithfulness, there are also hybrid approaches, which I'm not really like a fan of, but these are personal opinions, so this is a disclaimer. And I've had like a bit of a heated discussion last week during the Explainable AI conference, because people were measuring faithfulness using not confidence, but accuracy. So on the y-axis, they were using accuracy. So instead of measuring confidence, you measure accuracy. And why this is not really faithfulness, maybe some of you can have an idea on that. So why, if you consider dropping accuracy instead of dropping confidence or prediction, you're not measuring faithfulness? Sorry?
You just like accuracy based on matches.
Yeah, exactly. So
But I wouldn't say that this is really the issue, but the problem is that you're not testing how much there is like a change in prediction in the sense of how sensible are the features from the model, but you're trying to measure how much the model actually learned, the degree to which the model learned the features that it must learn. So this is something else. It's still meaningful, it's still sensible, but it's not faithfulness. Because in the moment you include the ground computation, you are conflating two properties. One is faithfulness, and the other is coherence, which is semantic alignment between what the model has learned and what you expect it to learn. Is this clear?
But I think we make confidence that then you have confidence by getting the sufficient result.
Yeah.
It means that zero probability of this collection.
Yeah.
But it's the one probability of plus,
No, exactly. But you can do a sample study in the case. So here we saw examples of one single image. Of course, if you want to expand it to 1,000 images, you take averages again. But you can actually do something like on these 1,000 images, if you remove 50% of the pixels, the accuracy drops by something. On a single image, you can say it's either 0 or 1, as you were mentioning in the beginning. Yes, of course. So do you have questions on this specific point? It's very subtle, the difference. Maybe it will be clearer when we talk about coherence. And the second point is that prediction gap. So instead of, we still do perturbation, but instead of perturbing by removing features, we perturb using random noise, and then we measure the prediction changes. And again, the question is why it is not really measuring faithfulness. Yeah.
I think because you don't actually see the effect of the feature itself, but the effect that the noise might have your model.
Exactly. So basically, if you do random perturbation, especially if you have sparsity in the explanation, it's very probable that you perturb in the direction of features which are unimportant. So you actually observe no change in the predictions. So there is no link between the level of importance and the change in prediction. So this is, again, a problem. And I posit that random perturbation should be used only in the computation of robustness, which is the next approach we're going to see after a short break. So wrapping up faithfulness, fundamental property, quantifies the level of alignment between explanation and model. Computation is complicated and controversial. You see a lot of different approaches. Some of them work better than others. But the main approach is this incremental feature removal. This is actually the chart that we observed using IROT on the embedding space. You can see that it's actually decreasing. What my student observed on the regular computation of IROT instead, with the one with the one instead in which we're considering confidence, we saw something like this, which doesn't make any sense. So all existing summary metrics for faithfulness are flawed. Some of them, they don't really abide to all of the assumptions which we have on faithfulness, and feature removal is often problematic because of the out-of-distribution detection issue. And this is an open research field in which, in my idea, there can be a lot of contributions from different profiles. Yep.
So we said how we can try to quantify faithfulness, but as you said now, there are a lot of flaws.
Yeah, of course.
So we use it because it's the best thing we have, or because combined with the other attributes, it makes it more robust?
I would think that still, if the current prediction, if the current metrics are flawed, yeah, of course, but they're still better than nothing. And you can still kind of use them to do like a one-to-one comparison, a head-to-head comparison. So you'll never have right now a real relative metric for faithfulness that tells you this is good, but you can still say this is better than others. Yeah. So it's still better than nothing in a certain sense.
a remark on that, but if we have different methods to calculate faithfulness, and one algorithm uses the one method and the other uses another method, so this comparison would be perhaps unfair.
I mean, in the end, you still have to fix one metrics and use that. You can use multiple metrics and do some sort of like Pareto study because it's multi-objective then in a certain sense. Or you can see if there is effectively one metric, like for example, SHAP, has the potential for being highly faithful the way it is constructed. In the sense that you already have perturbation, you look at prediction changes. The problem with SHAP is that we have like with 4 variables, we need to do 16, to calculate 16 different predictions. Let's say if you have an image, this image will be like 224 times 224. How many features is that? That's not combinatorial, that's combinatorial. It's an explosion of computations you need to make. And the extension of SHAP for deep neural networks are still an approximation. Yeah. Good. So let's take one last break before we go on to the other metrics, and this is going to be like a slightly lighter part of the lecture. The faithfulness was like really the most important formal part.
We're going to do part by part.
It's for love.
Have
Video. Okay. Okay, good. So while we wait for the others to return, we can talk about robustness. So robustness, we already mentioned it before, and it's a property related to perturbations. But the question is perturbations of what? So what can we perturb out of all the system of like the system of a prediction of a machine learning model? Yes.
The weights.
The weights, yeah, that's something you can perturb. There are three things that I can think of. So one is the weight. Then what can we perturb? Oh, yeah, I restarted everything. That's, yeah.
Can we start it?
Yeah, exactly. But I want to finish before 7. I actually want to finish like by 6:40 max. So yeah. So we can perturb the weights. What do we can perturb?
Of course, the inputs.
The inputs, yeah. And there's one more thing we can perturb. The only thing which is missing out of the model, the system model. So we have an input, we have a model. Yeah, exactly. So we can perturb input data, the model, for example, either by perturbing the weights or by changing the model, and the labels in the case of classification. So we can tell the model, generate an explanation of a dog instead of an explanation of a cat. And what is the desiderata? So what we want to observe for evaluating the quality of an explanation. So if I perturb the input data with small perturbations, what am I expecting in the explanation? Yes.
We don't want the explanation to take.
Yeah,
it's more explanation.
Exactly. So we want similar explanation. What about the model? If we perturb the model or change the model, what do we expect in the explanations? Yeah.
If the model behaves similarly to the other, also the explanation.
Exactly. Generically, we want a similar explanation. What about the labels? If we change the labels, what do we expect? All different, exactly. Different explanation. I think this is quite logical. But let me know if you have questions. So, how can I measure the similarity between explanations? So there are different approaches. One is overlap based. So I have generically, if I have two areas, B1 and B2, I can conclude their overlap by intersection over union. I think you all know about it. So take the intersection of the two and I divide by the union. A higher IOU means higher overlap. Of course, exactly. This means you need to be thresholding that, which is always very sensitive because you don't know, when you do threshold on 0.5, do threshold on 0.2, what you can do is the threshold, do multiple thresholding and do similar approaches to what you have before. So area under the curve, area under the curve. Otherwise, you have also this notion of continuous intersection over union, in which you take like pixel by pixel the areas of overlap and you measure how much they match essentially. And otherwise, you have norm-based approaches. And in this case, you pixel by pixel, you compute the difference. In some cases, norm-based is quite appropriate. In some other cases, it's not. Norm-based, like a generic version of a norm. So for consistency, I can, since the input image is the same, I can safely use intersection over union or norms. Norms is quite a good metric in this case. This is consistency. Consistency, of course, refers to the model perturbation. Contrastivity is a label perturbation. And the case is the same because I have the same input data. And I just want to observe difference in this case. So before I want the small distance with the consistency, with contrastivity, I want the large difference instead. And for continuity, instead, I have to take into consideration one thing, the sense that the two inputs are different. So I should relate the change in explanation to the change in input. So the higher the change in input, the higher I can allow there to be a difference in explanation. So these are all metrics which are based on Lipschitzianity. The idea is that small changes in input should cause small changes in explanation. One is considering the input, relative input stability. So you relate the change in explanation to the change in input. Well, delta is the perturbation. RRS is the relative representational stability, where you calculate you consider the change in the embeddings. So what is coming here after the convolutional neural network. And then you have relative output stability, in which you just compute the difference between the outputs. These are all three complementary matrices. I would say that relative representational stability makes the more sense, because in the end, what matters is how different the projection of the neural network changes between original input and perturbed input. But all these metrics have a huge issue that are highly numerically unstable. So take a look at the y-axis here. This is log stability. And this is like log 10 stability, which means that like sometimes you get like 1 times 10 to the 15 value, and sometimes you get 1 times 10 to the 5th. So it's very unreliable. You know that when you deal with big numbers, the density of the float representation is so small there that you can get wildly different results. And generically, I never trust measures like metrics based on Lipschitzianity. So the problem also lies in the plausibility of the perturbed data points, because in some cases the perturbations create implausible data, which is not what you want. So there's this, actually this former colleague of mine, Ilaria Vascotto, she proposed a nice method, which is based on the manifold hypothesis. I will try to go very quickly through it. So the idea in this case is try to stay within the data manifold. So you have a validation data set, and you project a data set, and you generate clusters on the projections, and you take the medoids, which are basically the centroids, but considering also the potentiality for categorical data. And you build a neighborhood of medoids. So you build, for example, like a neighborhood of 3 medoids, and this is the neighborhood for this specific medoid. Each medoid has its own like nearest neighborhood of medoids. And basically the idea is to generate perturbations alongside the medoids. So when you take a test data point, let's draw it in another color, like something in blue. So for example, this lies here. You take the closer medoid here, and you sample medoids in this neighborhood. So you can generate a data point on the line between here, on the line between here, and on the line between here, randomly chosen. And this is similar to what we saw before at integrated gradients, where you have this notion of linear interpolation. And this guarantees up to a certain degree that you stay inside the data manifold. And so this is the way, the formal way you generate the interpolation. Also, another thing, you discard the generated perturbation if the prediction, the predicted class changes, or the prediction changes too much instead of in case of regression. And then you basically measure the alignment between the explanations by mean of correlation. And of course, it's a rank correlation, so you don't take the Pearson correlation, you take the Spearman correlation. So all of this to be able to have a consistent metric, which is not numerical and stable, because the correlation is always between -1 and 1, so you have small numbers, and to generate feasible data. Yes?
I'm not sure, but Does this have to do with the convexity?
Probably, I'm not a topologist, so I think that
The
yeah, I mean, yeah.
it's a convex
yeah,
computation.
this is a linear interpolation, so you want to stay inside the yeah.
So we're not sure that it will be.
Yeah, we're just increasing the probability for that. Instead of perturbing randomly, we perturb in a specific direction where we hope there are other data. Okay. Then connected to robustness, we also have the disagreement problem, which is some sort of connected with consistency, so the model perturbation, which is that different feature attribution tools can exhibit substantial disagreements in important features. So this is an example from my first XAI paper, actually from one of my thesis students back in 2023. So these are figures of printed circuit boards, and these are 8 different variants of GradCam, and you can see that some of them are highly different, highly different features. Like look at age, for instance, how much it changes. So in order to mitigate a bit of this inconsistency between the different explanations, you can use ensembling. So there are several procedures in which you do normalization and aggregation of explanations, so that you run multiple of them, you merge them into one, and this has proven to increase robustness overall. And also, it's basically a technique based on consensus. The same thing as you do for ensembles when you have multiple machine learning models. Okay, so we're done with robustness. We have cognition now. And so the idea is that, again, we want an explanation to be human understandable. So which are the characteristics that makes an explanation human understandable? I found 3 of them. So let's see if you have some ideas.
Should be verbal explainable.
Oh, there is one step ahead. We can use LLMs right now to generate verbal descriptions of explanations, but LLMs are black boxes. So again, we're sweeping the dust under the rug. Yeah.
Maybe it should align with common knowledge.
Yeah, that is coherence, actually. So this is just the way you present the explanation. Yeah, to be more clear what I'm asking now. You can refer to somehow to counterfactual explanations as well.
Yeah, it should be like distinct.
Yeah, but this thing can be also more like, yeah.
I thought of something. You need, it's, I don't know, borderline. You need different explanations for different class, so you can't have features, the same features be important to.
Yeah, this is also part of presentation, but let's restrict, like, we have only one explanation, so we don't consider more of them. So based on only one explanation, we have to somehow evaluate it.
I think it's quite like, because our so much like prison and cows. Using Casa.
Yeah, but this is also very complicated. Let's think about it in a simple term. So small, of course, exactly. That is always important. If you have a tabular data set with 100 features and you say that 70 are important, then it's very complex. So you want like 2, 3, 5, 10 important variables. The more you add, the less understandable it is. Small size. Then what can we think about them? Yeah.
Maybe a metric, a score value for the human to understand.
Yeah, but
maybe we can get that you want 1 and not 0.
Yeah, exactly. This is polarization. Yeah. So you want values that are not 0.5, but close to 0 and close to 1. And that is complexity. It's something that we have discussed several times without really going into details. Feature interaction. You can have feature interaction in the explanation, but it makes it very complicated to explain to humans. So let's talk about size and polarization first. So of course, the larger the explanation, the harder it is to understand from a human perspective. And we already saw this in the counterfactual with sparsity. Polarization should be as close as possible to 0 and 1s. And this is the work of Krabbe and Michaela van der Schaal. So this is the desiderata for an explanation, especially if you're on tabular data. This work is specific for time series data. We had a question for that before. So what we have here is we have very few features which are important, and their value is as close as possible to 1, while the non-important features are as close as possible to 0. B is the opposite. It's very dense, but still very polarized. C is sparse, but there's a lot of in-between values. And D is exactly what we do not want. Big explanation with a lot of in-betweens. So the way you can measure size is, for example, with the L0 norm, which counts the number of non-zero terms. So this is low norm, this is high norm. And polarization, instead, you can measure it with entropy. So the more sharp the explanation is, the lower its entropy. Entropy, you can correlate it with chaos in this case. The more chaotic an explanation is, the more difficult it is to understand. And there's also an additional term, which doesn't appear in this work by Krabbe and van der Schaal, which is redundancy. And you have some information theoretical metrics to use. And you don't want, like, for example, if you have multiple of the same features in the explanation, you don't want basically the explanation to contain all of these features repeated. Okay. Complexity is instead deals with feature interaction and feature disentanglement. And this is connected again to features being highly correlated with each other. But let's concentrate on feature interaction for a second. Do you have examples of feature interactions? Can you think about examples of feature interaction? How it can come into play?
Feature interaction, feature.
Yeah, so an example in which you have like a meaningful feature interaction is, let's say you're running a facility that rents bicycles. And you want to predict how many bicycles you're going to rent on a given day. So you create a data set, you cross-reference the number of bicycles that you rented with meteorological data. So you can have, for example, temperature and wind speed. So what you can think of, like for a temperature, you're going to have like a sweet spot. So if the temperature is very low, you're going to sell very few bicycles. So you're going to rent very few bicycles. And if the temperature is very high, you're going to have the same. Like, for example, 30 degrees, above 30 degrees, you're going to rent very few bicycles. And probably below like 2 degrees, you're also going to rent few bicycles. So there's some kind of like a linear relationship. And for the wind speed, you can think about something linear. Sorry, maybe the opposite, not this. I think I have. Wait, yeah. So the higher the wind, the fewer bicycles I sell. But I can think about also a way in which features can interact. Because if it is very warm, but there is like a high wind speed, actually I will observe more bicycles being rented because the wind makes the perception of the temperature smaller. And vice versa, with wind and high temperature, I could observe in like a steeper decrease. Because you have a low temperature, very high wind, I could actually rent even fewer bicycles. So this feature, they contribute more than they actually do separately, more individually. And there's a lot of examples of feature interaction in medicine where you want to explicitly model it. And there's a lot of examples, and also deep neural networks are able to capture very complicated feature interaction. This is a second order feature interaction. You can have n order feature interaction, which already took us like 5 minutes to explain 2 order feature interaction. 3 order feature interactions are basically impossible for humans to explain. And you can have tools like, for example, SHAP IQ, which is SHAP with feature interaction. You have, for example, the interplay between latitude and longitude for the California housing data set, in which you see that latitude has a positive contribution when in conjunction with longitude there's an even higher contribution. So you have to think, do I provide feature interaction in my explanation or do I not? Because if I do, it's going to be very hard for a human to understand it. So this leads the way for a fundamental trade-off in XAI, which is the faithfulness cognition trade-off. So the more compact and less complex an explanation is, the more human understandable it is. But on the other hand, the fewer features and the less interaction term we include, the more unfaithful this is. This means that essentially, according to the problem we are modeling, there is somehow like a theoretical gap that tells us if you don't include feature interaction, you basically cannot have very faithful explanations. And be careful that faithfulness is not only a function of size and complexity, it depends on the tool. Because if you GradCam has no theoretical foundation, so it can create very unfaithful explanations, even if there is not a lot of interaction in the interplay between figures. So final part is coherence. I think this is like the simplest one that you could expect. So in image classification, for instance, you can have segmentation maps, and there are a lot of data sets with segmentation maps, and you can check like how much of the explanation is actually present in the segmentation map. It becomes much harder for image regression. Which ground truth do we have in this case? What can you say, like, for example, which should be the important features for determining the age, for predicting the age of the person? Or even worse, what should we do with text generation? Which are the important features in text generation that you can say, yes, this model is actually reasoning correctly? Or even pixel level image regression. An example is depth estimation. You correlate for each of the pixels in the image, you have a prediction between 0 to 1, which tells you the depth, relative depth according to the camera. So this is the ground truth. And how do you expect, what do you expect the model to be looking at when explaining depth estimation? Maybe you have further examples, but you can see how it is hard to obtain ground truth for explanations. So takeaways for coherence. Ground truths are not easy to obtain. They may be impossible to obtain in certain cases. Maybe in this case, you want to run user studies because humans can actually tell you in this case if an explanation is coherent or not. So this is the final chapter, just a few slides. So a few indications for sample studies. It can be tricky. Why can it be tricky? Because the concept of good explanation is ill-defined. There are several characteristics you might explain. This is an example in my idea of bad user study from a paper, this paper from Merkel et al. So which algorithm is more reasonable? It's clearly more reasonable. One is clearly more reasonable. One is slightly more reasonable. They're the same, slightly more reasonable number 2, or clearly more reasonable number 2. What does reasonable mean? Does it mean it's capturing the dog? Does it mean it's a big explanation, a small explanation? So a human doesn't really know that. So solution could be, for example, separate the evaluation in multiple questions. Instead of asking which is more reasonable, you define different characteristics that humans have to evaluate. Some characteristics cannot be evaluated by humans. Do you have some examples? What can a human evaluate of an explanation of the things we saw until now? Like
a human or an expert?
anyone, yeah.
I cannot tell from an X-ray if the person has cancer or not.
Yeah, but this is even.
So you evaluate.
How can you evaluate the faithfulness? How can a human evaluate the faithfulness? You need, it's the typical example of an explanation, sorry, a quality that you need to evaluate functionally. So faithfulness, robustness, you need to evaluate them in a functionally based way. And so you need to split something you have to run in a functional way, and some things you need to evaluate with a user study. And be very clear. For example, it's completely useless to provide an unfaithful explanation to a human because it's not aligned with the model. And also, this is something that I noticed that a lot of people in XAI do because they usually come from computer science, and in computer science, you rarely study statistics in a rigorous way. Sample size, sampling methods for determining the sample of people that are participating, the tools to check for significant results. This is based upon science, which has been developed in 400 years of development. And somehow people still don't know about it. So my suggestion is, if you want to run user studies, use statisticians because they know what to do. And for example, I reviewed a paper last month in which they run a user study and they just provide an explanation and they said evaluate it from 1 to 5. And they concluded our evaluation is good, our explanation is good because the user gave it an average of 3.5. It means nothing. You're not comparing it against anything. The sample was all grad students and PhD students. So they didn't provide any sort of statistical significant results. No, nothing. Okay. Good. So also another thing to do, don't run only functional evaluations. Check with your eyes that the explanation makes sense. You can have very faithful explanation, but they don't make any sense to you. So take randomly 20, 50, 100 images or 100 data points, generate the explanation, check all of them, and don't do cherry picking. Because if you cherry picking, you bias the evaluation of the model. And to conclude, this is the Bible of the evaluation of explainable AI, the paper from Nauta, from anecdotal evidence to quantitative evaluation methods. You can see that actually here the properties are not 4, but there are 12 of them. Some of them you already know: consistency, continuity, contrastivity, compactness, coherence. Faithfulness is split into parts, correctness and completeness. And if you want to experiment more with explainable AI, I highly suggest you read this paper, and this checks only for other type of XAI methods, not only feature attribution and counterfactual explanation. So to recap, evaluation of counterfactuals is usually included in the generation process. So it has similarity, sparsity, predictability, actionability. So we identify 4 main areas for feature importance: faithfulness, robustness, cognition, and coherence. And Nauta define this like code 12 properties. User studies are important, but they're often noisy, and goodness of explanation is ill-defined. So you need to be very thorough when you design user studies. Quality evaluations are good. It's not because they're scientific we shouldn't do qualitative stuff. This is very wrong in my idea. And yeah, the presentation is over. It's 6:35, so perfect in time. Here are my contacts. Please keep in touch. Send me an invitation to LinkedIn. If you prefer more conventional chatting, use my Telegram handle or my email. And yeah, thank you very much for attending. And I hope to receive some questions from you, and also further, if you want to do XAI in your research, please let me know. Great.
Thank you very much.
Thank you. Here you have references. You will see them in the slides. The one in bold are those that I recommend if you want to get to know more. So you see the one from time series, the one for feature interaction, feature visualization,